there are the, you see, I should have done it.
It's good.
Andrea, just send me. I'll take care of it.
No, I know I have to send you, but so when I export it to PDF file, the hidden slides were included. Let me PDF.
Alberto.
Yes.
I have a question.
Oh, no, I have to manually.
Here in the webinar that says that we are in a practice session. That attendees cannot join until we start the webinar. Are we starting sharp at 10 a.m.?
Well, the starting time is 10 a.m. That's the idea. I don't know the start webinar thing.
So right now what's happening is, yeah, what happens is we're kind of, all the folks that are on the participant list, we're all inside the meeting right now. At 10 o'clock, I'll start the webinar, and then that's going to let the folks on the attendees side in.
Okay, that sounds good.
When I do, go ahead, Juan. I was going to say what I'll do is I'll start, if you want in like a minute, I could start the recording and I'll start the webinar, and that'll bring everybody inside. But just want to give everybody a heads up that will be broadcasted at that point.
Okay, thank you.
You got it.
Juan, your chair. So let us know when you want to start that as well.
We can start 1 or 2 minutes before starting the slides.
Okay.
Right now I'm throwing a message in the Slack reminding that if they can enter, would be nice.
No, it does not seem I have the privileges to upload my slides, so I will email it to you, Alberto.
Yes,
is that
and
okay?
then I upload. Yeah. Then while you talk, as quickly as I can, I will put them online.
Sure, sorry, I didn't get a chance to do it in advance.
Juan, send in Slack a reminder.
I'm
Not
doing
so
that.
many people.
Just it.
I see. Very good.
Later after the lectures.
Sorry, I missed that.
So I said I have a single file for both lectures today. I will maybe split it later on.
Well, just send it me to now, whatever you have, so the students can follow.
Yeah.
Then we can adjust.
All right, I'm going to start the recording and I'm going to open up the room.
Andrea, did you send it?
Yes, I did.
Okay, I did not receive it yet.
It's 5 megabytes.
Okay, maybe it takes a little while.
So can I ask you, Alberto or Juan, how does it work with questions, for example? If the students have any questions, they can interrupt me during the talk, right?
Good point. We have been working the following way.
Yes.
The Hawk students that are in the call, they can raise their hands at any moment, and either me or any of the hosts will interrupt you. Andrea, we have a raised hand, and then we open the mic to
Okay, so
answer the question.
okay, so I will pay attention to either you or Alberto, for example.
There is another. In some cases, they can also write the question in the chat. In that case, we can read it to you, or you can open it and read it. But
yeah, because I'm not sure I can see the chat while I share the screen. This is one of the things I've been fighting.
Either me or Arun can read the question. Then.
Yeah, all right, okay. Oh yeah, there is Arun as well.
Yeah, there is also people. There are also some attendees from outside Hawks from the REYES program. They cannot raise a hand or ask in the video, but there is a Q&A session section of the call, and we call if there is questions in that area, we bring them by the end of the session.
Okay.
So that's more or less the dynamic. I don't know if you want to add anything else, Alberto.
Just it is time to start. And I have not received the slides from Andrea.
Oh, I'm sorry. I mean, I've sent it to your JLab account from my university email address. Maybe it's I don't know. Well, it doesn't like it. I can try to send it again.
Yeah, send it also to Juan and Arun.
Yeah.
Yeah, let me see.
And then we start. It's becoming late.
So Juan. Oh, I don't have your email in this computer. Juan VG. Juan VG at JLab.
Yes.
.org. And Harun?
It's Arun TS.
Okay, I received it. Don't worry.
Oh, great. Sorry, guys. Yeah.
Let's start. Juan, it's your call. Go ahead.
Okay, let's start. When you want, you can start sharing screen, Andrea.
Okay. So. And I think I've lost track of the I've lost track of the participants tab, but okay, it doesn't matter. Actually, so before sharing the screen, I just wanted to no, let me see here, participants. Okay. Yeah. Yeah, so I guess the students are connected, right? You can all hear me well.
Yep, we can hear you and see you.
Okay, great. So I just wanted to have like a brief meet and greet sessions with all the students, because I mean, it's pretty difficult to, I believe, lecture online. So I mean, I would really love if we could for a second turn on the camera and see each other in the face just for a few seconds. Let me see, now my screen is frozen. Let me see, okay. All right. So yeah, you know, I mean, I think since we are gonna spend a few hours together talking about cool physics, I just wanted to say hi to all of you and ask you, how is it going up to now? How do you like the school so far?
I think this has been a really cool experience so far. Glad we're doing this.
Okay, nice. I think I don't know. I was reading through the name of the attendees of the school. I don't know you guys, so I mean, it could mean many things, but one of the things it means is that I'm getting old. So there are many new students in the field, which is very nice. So let me tell you like a couple of things about myself. My name is Andrea, as you surely know, and I've been working on TMDs and hadron structure in general since a few years. I did my PhD in Amsterdam with Piet Mulders, And then I moved to the States, working in Jefferson Lab and in Argonne National Laboratory on the physics of transverse momentum distributions and on hadronization. Now I'm at the University of Pavia in Italy, which is my home country, and I'm working again as a postdoc here with a European fellowship. But okay, this is about me. I mean, it doesn't matter too much. What I wanted to say is that, I mean, I've been working on these things for a few years. What I will try to tell you during these hours is what I've learned during these years, not everything, of course, but also I think it's pretty challenging to try to convey the message in a more or less uniform way to students with a different background. So let me try to understand, like, how many of you are experimental physicists? If you can raise the hands with Zoom, for example. Let me see here. All right, 2, 4, 6. Okay, I see. And I guess the rest are theorists, right? So I see 50 people, more or less, like 50% or a little less. Okay. So, I mean, who among you has a working experience with TMDs? 1, 2, 3, 4. Okay. 5, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Good. No, I mean, it's a good number. So, all right. And so you more or less have an idea, probably even like a deeper understanding of what I have about these things. So in general, also for the people who don't have a working knowledge on Teams, what are your expectations for these 5 hours? What do you think you would like to know? Or is there like a specific topic that you would like to hear today or tomorrow or in the recitation sessions? Is there something that really makes you say, okay, I have to attend these lectures? Just don't be shy. Tell me something. We'll see if we can make it.
Guys, you can either type in the chat or you can raise the hand and talk. It's fine.
I'll talk, but I can't really answer that question considering the fact I don't know much about TMDs, so I wouldn't know what.
Wait a second. You are? I don't see from the participants.
Caleb Vogler. My video should be on, so you should be able to see me.
Let me see. Okay, Caleb. Okay, hi. Nice to meet you.
Yeah. I don't know much about TMDs, so I'm just hoping to learn more about them. So I can't really say specifically what I want because I don't know enough about them. So.
Okay, that's fine. Anyone else?
I'll say something similar to Caleb. My name's Andrew. I'm excited to do our first lecture, an introduction and an overview, and I think after that I'll be able to give you a much better answer as to what I'm doing.
Okay, great.
We have a raised hand by Daniel Adamias. Go ahead, Daniel.
Yeah, I would like to see at least one detailed derivation or work through problem so that we can get our hands dirty with the calculations to really get an understanding. Okay, we'll probably have that either in one of the lectures or in one of the recitation sessions. Most probably, I think, in the recitation sessions, because, you know, I mean, with this kind of lectures online, it's a little bit more difficult to like sit down and work out a detailed calculation. I think it's just a way. It's just the way I relate with the screen. Probably it would be easier in a classroom in front of the blackboard, so that I can see if anyone is getting lost or if anyone starts doing anything else, you know, these kind of things. But probably we'll see. I was thinking about, for example, the derivation of the sign change relation for the Sievers function, working out all the details, and maybe I can provide notes about that as well, so that if we don't make it during the recitation sessions, you can have something to read later on. Sounds great.
Good. Anyone else? Rafael?
Yeah, first of all, let me say hi, Andrea, because we've been briefly working together with Ignacio and Miguel in the...
Yeah, I know, Rafael, yeah. That's true.
And yeah, but the question, well, for me, it's good to, I don't know, look at the theory through someone else's lens and see, I don't know, how you approach the thematic of TNDs and all of that. It's, I don't know, I think it's interesting to know different points of view. Yeah, and getting dirty about the calculations and, as you said, the example from the Sieverts function, that seems interesting to me.
Okay. Yeah, I know, for example, you, Rafael, have been working with the soft collinear effective theory approach, right?
Yeah, that's right.
Yeah, okay. So we will not cover it during the lectures, but I will use like a different approach. I will mostly not talk about, derivations of factorization theorems, but we are going to talk about it. I mean, the topic itself, as you well know, is like complicated and very detailed. It might not be like the best thing to tackle during an online lecture, but we're going to touch it.
Yeah, I agree.
Okay. Let me see. Anyone else who feels like sharing like desires or interests? Well, okay. If not, I think we can get started with the real lectures. So first, thanks for sharing your thoughts. I mean, it's going to be useful also for organizing the recitation sessions. And as I said before, I mean, feel free to interrupt me during these 2 hours, or well, during the first 15 minutes, and we'll see where we can get today. All right. Okay, can you see my screen?
Yes.
Not yet.
No, actually, no.
Not yet.
So
It's thinking about it.
It's thinking
there it
about
is.
it.
yeah.
Okay.
Yeah.
All right. Okay, so now that we more or less know each other, let me give you like a very general and very brief introduction about why we should do these kind of things. Why do we want to study hadron structure, hadron formation, and especially why we are talking about transverse momentum imaging. So this is a very nice slides that I often use at the beginning of my talks. I really like it because it reminds me that what we are working on is a very interesting object that lies at the boundary between macroscopic physics and microscopic physics. So hadrons live really on these boundaries between what we can calculate with elementary particle physics in the standard model and what is shaped by the properties of these particles, like, for example, chemistry or condensed matter physics. We can interpolate from the property of hadrons until we reach like the scale of our daily life. So it's really, I think it's really fascinating to look at these kind of structures for many reasons, but personally for me, this is the most important one. And also the fact that protons and neutrons that we will call nucleons in these lectures, they make up more than 99% of the visible mass in the world. It's like a good motivation why we should understand these kind of structures. So the theory we have at hand is quantum chromodynamics, right? So quantum chromodynamics tells us how to calculate the properties of quarks and gluons, but does not really teach us too much about directly about the properties of hadron. Namely, if you want to understand something global about hadrons, like, I don't know, for example, the mass of the pion or the mass of the quark or their spin, their size, it's pretty difficult to do it starting from the QCD Lagrangian. But I mean, this is not really satisfactory. It's like a deep mismatch between our tools and our goals. So I think the most pressing and most important questions we should try to understand are the following one, namely understanding the mass, the spin, and the size of hadrons in terms of the degrees of freedom of the theory, understand hadron formation and confinement, namely why quarks and gluons live only inside hadrons, they cannot be found alone outside of a bound state. And also trying to understand the structure of hadrons has implications and consequences. It's like an important question. I mean, do we really understand how the dynamics of these quarks and gluon and their motion in momentum space, their distribution in momentum space, or even in coordinate space accounts for the global properties of the hadrons? So as I said, I mean, before now that once you have identified the question, you should ask yourself how you want to tackle the problems, right? And especially how you want to use your theory. So you might want to say, okay, I have a quantum field theory like QCD. What I can do is compute an observable by sitting down and taking pen and paper or a powerful computer algorithm and calculating all the Feynman diagrams that I think contribute to a specific observable, right? And my observable, oh, by the way, can you see my pointer?
Yes, I
Yes.
see it now.
So a specific observable O at a specific energy scale Q can be computed as an expansion, a series in powers of the coupling constant alpha of the theory. So alpha tells you how strong is the interaction between quarks and gluons and among gluons themselves as a function of the energy at which you want to compute a specific observable. So suppose you want to calculate something which is related to the nucleon mass, which is around 1 GeV. So can you tell me if this works or not? Let's start from the easy things. Let's start from the basics. Can you use such an approach if you want to calculate the nucleon mass, for example?
No.
No, and why is that?
QCD is non-perturbative. It's alpha S is too big.
Yeah, exactly. So this is exactly the reason why that approach fails if we want to compute quantities at non-perturbative energy scales, at low energy scales. The coupling constant of QCD alpha S is very large at low scales. So if you are at high energy, then the perturbative series converges because alpha is small. But if you are like around 1 GeV, Q is around 1 GeV or between 1 and 10, you already have troubles because that coupling constant is too large for the perturbative series to converge. So we need to do something else. And it's not that we have to abandon QCD, but I mean, perturbative QCD is not the only approach. There are different techniques. One can use lattice QCD, for example. I'm sure you're gonna hear more about it in the coming days. You can use other effective theories of QCD, which are approximations of QCD that work at low energy, or you can use model calculations, or you can use phenomenological approaches that combine perturbative QCD with information coming from the experimental data. And this is what we're going to focus in the rest of the week mostly. So when we talk about hadron physics, there are, as I said, two macro areas to investigate. The first one is the area of hadron structure, namely how to describe the properties of hadrons in terms of partons, namely in terms of quarks and gluon. The second one is hadron formation, namely understanding how hadrons are generated dynamically from the quarks and the gluons themselves. This is also called hadronization. And I've been focusing on this side like in the last 1 or 2 years, let's say. So here, think about, for example, what happens when a quark is liberated from a hadron, from like a proton, for example, in a deep elastic scattering event. The quark is knocked out of the target, but it cannot reach the detector as a quark itself. It has to recombine or combine itself dynamically into a hadron. And this mechanism is called hadronization or hadron formation. And it's a different side of confinement with respect to hadron structure, but it's, I mean, as important or even more important, if you want, than hadron structure itself from the point of view of the questions that we outlined before. So in order, I mean, the reason to do this is first of all conceptual, right? Because we want to understand QCD. We want to understand how the world, the universe works. But also, there are many practical reasons, because around the world, there are many different experiments that scatter hadrons and measure hadrons in the final state. So we have to control very well. We have to have a detailed understanding of hadron structure and hadron formation if we want to do precision physics with these experiments. Think about the LHC, where they collide protons and they look for signatures for beyond the standard model physics. Looking for particles with a very high mass means that you have to know hadron structure at very large X with a lot of precision. If you don't have this precision, and actually we don't have so much precision at high X, your results, your searches for physics beyond the standard model might be hampered by this ignorance of hadron structure. So it's very important that we get proper understanding of hadron structure also for this. And think about it. I mean, I said that more than 99% of the matter in our world is made out of protons and neutrons. So if we could understand how quarks and gluons interact together and they combine, that they govern QCD in the same way that we control electrons and photons, I mean, I think the technological consequences would be unimaginable. We would be able to control like the rest of 99% of the energy which is stored in matter. This is a bit speculative, but I think in a school we should also tell you these things. I mean, there are very deep reasons why we should try to understand QCD, and one of these is that we may be able to improve our world and our society as well. But okay, so apart from dreams, let's go back to the realm of hadron structure itself. And this slide is meant to tell you that there are different, many mathematical ways to categorize the information about hadron structure. So there are many different correlation functions or pattern distribution functions that you can define. This slide is not, I'm not going to tell you everything about all the functions in this slide. This slide is taken from a paper which is called Introduction about TMDs and GPDs by Marcus Diehl. It's a very nice paper. I really recommend it if you want to get an overview of the differences and the relation between these two maps of hadron structure. And each of these functions encodes something about a specific property of hadron structure. In the lectures, we're going to talk about mostly PDF and TMDs. So the bottom left corner here. But as you see, the world of hadronic physics is much more complicated than what I'm going to tell you in these days. So feel free to ask if you have curiosities about all the other functions. Maybe I'm not the right person to answer them because I'm not that expert about it, but maybe we can talk about it and I can point you to references. And of course, you should ask also the other lecturers, for example. So let's focus a little bit on the TMDs and the GPDs. So the very first function that I have here on the top of the screen is the Wigner distribution. The Wigner distribution is a map in both momentum and position space, where you're sensitive to the collinear momentum of a specific part and the transverse momentum and the transverse position. If you integrate out the information on the transverse position, you get a TMD distribution where you're sensitive to the collinear momentum fraction of the quark inside of the nucleon, like X, and the transverse momentum of the quark. If you integrate on the transverse momentum, you get only information on the collinear momentum fractions of your parton, so the so-called parton distribution functions. If you integrate out instead the momentum components, you go to the right-hand side of the slide and you have information on the GPDs and the form factors. But as I said, we're going to stick with the left side of the slide for the rest of the week. I guess you're getting lectures about DVCS and GPDs specifically, so I'm not going to talk about it. So let's instead say, specify what transverse momentum imaging means. It's pretty obvious, but it's better to specify that, right? So imaging means that we should start from some information, maybe some experimental information, like these points, data points. These are data from the COMPASS collaboration that measured semi-inclusive deep inelastic scattering namely the scattering of a muon on a target, producing pions and kaons in the final state. They measure the transverse momentum dependence PHT of the cross-section. And our goal is to get out maps of hadron structure from this data. So here on the right, for example, you see the contour plot for a transverse momentum distribution. In the plane, you have the information about the transverse momentum. You have the kx here and the ky components. And in the longitudinal direction, let's say, you have the x dependence. So you see how these maps in transverse momentum change if you change the collinear momentum as well. I mean, here I'm just telling you what the goal is, what the starting point is, and what the final step of your work is, namely getting images of TMDs. So the way to do it is pretty long and complicated, and we are going to see like a few things, some of the steps that are involved in this process. But let's first of all recap for a second and specify again what we're talking about when we refer to Parton distribution functions and TMD Parton distribution functions. So Parton distribution functions are maps of hadron structure in momentum space. Think about having your hadron that moves along the blue arrow here. A Parton distribution function tells you what's, in quote, the probability of finding a quark or a gluon with a specific longitudinal momentum. So a momentum that that's along the blue arrow, or the transverse momentum dependent PDFs tells you what's the information of having longitudinal momentum x combined with the momentum kt in the transverse plane. So you see, I mean, the F1, the collinear PDF is like a projection of the TMD object in a sense. Mathematically, this is tricky to show. Maybe we're gonna talk about it, maybe not. But what you should keep in mind is that the TMD PDFs, namely the three-dimensional distributions, are more complicated objects because they encode much more physics with respect to the collinear, the one-dimensional Parton distribution functions. If you talk about hadron formations instead, you have different maps, different functions that can collect information about the process of generating a hadron from a quark or from a gluon. According to what you measure in the final state, you can have a single hadron collinear fragmentation function, namely a fragmentation function that tells you what's the probability of finding, say, one pion from a quark, measuring only the collinear momentum fraction of the pion with respect to the quark. If you detect also transverse momentum of the pion with respect to the quark, then you have the TMD fragmentation function, namely you are sensitive to Z, the collinear momentum fraction of the pion, and the transverse momentum of the pion. You can also do more fancy things like identifying two pions, not one single pion coming from a hadron, and then you have a dihedron fragmentation function. Or you can identify a bunch of hadrons, and then you have an inclusive jet fragmentation function where you're sensitive to the invariant mass of this jet or the quark virtuality S. Or then, I mean, you can come up with many different things. Actually, I don't think we exhausted all the possible combinations yet. But you can also, for example, identify a hadron, like pion, inside of a jet, and then you have an in-jet fragmentation function. We're not going to talk about all these objects because it will need like a week, but mostly I'm going to tell you something about the first two functions here, the collinear and the TMD single hadron fragmentation functions, because those are the functions that we use when we study semi-inclusive deep elastic scattering. So these are examples of collinear and TMD Parton distribution functions. This is an extraction of collinear Parton distribution functions by the neural network PDF collaboration. These colorful bands represent the probability of finding a specific flavor of quark or gluon inside of a proton, and the width of the curve represents the uncertainty on the extraction on this probability. So you see here you have a distribution as a function of X, whereas if you talk about a transverse momentum dependent PDF, you have a distribution which is a function of X and K perp, and here you see the transverse momentum dependence of these distributions. So questions so far?
Does the
No.
plot on the right dip below 0? I can't, sorry.
Say it again, sorry.
Does the plot on the right dip below 0? It looks like I just
Yeah, it could be. It could be that it goes below 0 a little bit. So this is possible. I mean, it's a very good question. The answer is pretty long, but in a nutshell, I can say that it may happen. Because I mean, in principle, the PDFs should be positive if you don't take into account renormalization. But depending on the renormalization scheme and on how you do the evolution of these objects, it might be that some of them, let's say the unpolarized PDF become negative. There is actually a good chunk of papers in the literature that try to understand this thing, because I mean, it's might not really be what happens, but short answers, yes, it could be a little bit below 0. It might even be a feature of the parameterization, and within uncertainties, you see that it's compatible with 0. Okay, I'll.
You have 3 raised hands, Andrea.
Yeah, sorry, I cannot see the. Let me see chat. Yeah, please go ahead with questions if you have.
Hi, Andrea. I'm Simone Venturini.
Ah, Simone, hi.
I have a question, but in your neural network PDF model, I can see that C distributions depend on flavor. You know, different flavors have different distribution of the PDFs. Is it wrong to assume that, for example, the C is symmetric, or is only an assumption that we can neglect?
You mean if it's wrong to assume that, for example, S is equal to S bar?
Yeah.
So, I mean, in principle, in the proton, since we don't have strange quirks in the valence sector, I mean, you don't, so the difference between S and S bar integrated over X should be 0. But the two functions themselves might be different, I believe. So when you say that they cannot be in the valence sector, it means that their valence number, which is defined like the integral over X of flavor minus anti-flavor, should be 0.
While
so
in a meson, for example, a pion, is it possible to assume this symmetry? Or
I mean, you can definitely assume the symmetry. Yes.
Yeah. It's only a choice we can do in our model.
Yeah. I mean, it's a choice you can. It's a choice, as I said. Eventually, what should happen is that if you don't have that specific flavor in the valence sector, the integral of the difference should be vanishing.
Okay, thank you very much.
You're welcome. But if anyone has like a different opinion, then feel free to let me know. I mean, we are here to discuss.
Andrea, we have raised hands. I'm gonna go by the order that they came through a chat.
Yeah, let me say one thing first. I mean, I gave you, like in this introduction, a few different concepts, like slightly unrelated to each other. So don't feel lost if you don't get completely what I said. This was meant to be like an introduction, but feel free to go ahead with questions.
Yeah, the next question is by Arjun Kumar. Go ahead, Arjun.
Hi. So I was asking about this TMD's plot on the right hand side. So is there like the scheme seems to be Gaussian like all the 3 1. So is it in the parameterization that some input goes like?
Indeed, yeah. This is the yeah. It's precisely that. I mean, these shapes are not precisely Gaussian, but a combination of Gaussian functions, and it depends on the model that you choose when you fit the data, of course. This is also a 2GV, so it means that on top of the model, you have some effects from TMD evolution. So you don't really get to see the shape of the model at the initial scale, but definitely it can be whatever you choose in your model at the initial scale.
Okay.
In
Okay.
this case,
Thank
it was a combination of a Gaussian and a weighted Gaussian, if I remember correctly.
All right. Thanks.
Next raise hand is by Jorge Javier Urquiza. Go ahead, Jorge, please.
Hi, Andrea. I have a very, I don't know, maybe foolish question, but I don't know much about TMDs. But in these functions, you have a dependence of the momentum, the transverse momentum. There are two components. In these TMDs, you can distinguish between these two components, or they're fixed together, or they're symmetric. I don't know.
You mean X and K perp?
Yeah, something like that. But in the moment, like.
Yeah. So the what do you mean with distinguish? If you can separate the functional form?
Yeah, or maybe like the contribution is different in some range of energy. I don't know.
Yeah, okay. So again, it depends. So from the perturbation theory point of view, you cannot really separate the two dependencies. Then in the non-perturbative model that you choose when you fit your data, but I'm gonna talk about it better like in the next lecture, you can assume the X and K perp dependencies to be, let's say, factorized, or you can even assume like a dependence, like in this case, see that the transverse momentum dependence here changes with the value of X, which is represented by the different colors. So I mean, again, it depends on what you do, but I think I will be able to give you like a more proper answer like in the next lecture. I mean, on Wednesday most probably.
Okay, thank you very much.
Thank you, Jorge. Now we have a question by Ching Him Leung. Go ahead, Ching.
Okay, so my question is about the negative when the TMD goes to negative. So how should we interpret that region?
Yeah.
For PDF, we usually think about it in terms of probability, but if it goes to negative, how should we interpret it?
Yeah, well, I think the most honest answer is I don't know. I don't think it's a physical feature. I mean, from the physics point of view, since F1 has a probabilistic interpretation, it should stay positive, right? If it goes negative, it's because of an artifact of the theory, like the way you renormalize the PDF. This happens with other functions as well, but other functions are related, like, I don't know, the helicity or the transversity. Those functions are defined as differences of probabilistic configuration. So since they are a difference, they can go negative. There is nothing weird. You have other kind of constraints, which are called positivity bounds, that relate, for example, the helicity and the transversity and the unpolarized PDF. But in this case of F1, I believe it should stay positive. So again, maybe we'll address it more in detail in the coming lectures.
Right. I believe for NPDF, even the unpolarized version also goes to negative at some region of X.
Yeah, because it's the same thing. Okay, so the renormalization I was talking about affects both the collinear and the TMD PDFs. Here it goes negative in K perp, in the TMD part, let's say, but it can be as well in the collinear momentum dependence.
Thank you.
Okay, thank you. Now we have Caleb.
Then I think it's gonna be the last question. Otherwise, I'm not gonna tell you much today. But it's my fault. Go ahead, please, Caleb.
I'm assuming X here is Bjorken X, right?
We'll see that later, but yes, it is.
Okay, it's just that in slide 15 we had KX and KY, and I'm assuming that was spatial X and Y, but we also have X.
Yeah. So here KX and KY means the two Cartesian components of the transverse momentum.
And is that X?
It could be K1 or K2, for example. That's not the same X as the collinear momentum fraction.
It's just there's a lot of ambiguity when there's all these X's. And
I
sometimes
agree. I
mistakes
agree.
occur.
I agree. You're right. Sorry.
So is it mostly just BureauConnects though? Or
So okay, say for example, this one that I'm pointing to with the mouse here is BureauConnects. The one in the data where the data is the average values of BureauConnects. The KX here means like the first component of the transverse momentum in the transverse plane, but the X is not BureauConnects.
okay.
I should have named it K1 and K2, for example.
Thank you.
Okay. 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 Can you still hear me?
Yes.
Okay. So I'll move forward. So okay, here this slide is just to tell you that I'm gonna give you I'm gonna tell you two things from the theory point of view, namely that we need an operator definition for Parton distribution functions. I mean, in order to study these objects properly, we have to define them in a quantum field theory. So we need an operator definition. Say when we have a deep inelastic scattering process, lepton scattering of a hadron with a lepton in the final state, one can define the Parton distribution function basically by taking the square of this Feynman amplitude and calculating a Fourier transform of a bilocal operator. We are going to see how this definition emerges from the formalism itself in the remainder of the lecture. But this is to tell you PDFs have an operator definition, and this operator definition should be universal, in the sense that it should encode universal information about hadron structure. It cannot be different if it's calculated and measured for the deep inelastic scattering and then calculated and measured in Drellian. So the information about hadron structure has to be universal, otherwise we are doing something wrong. There will be 8 distributions depending on the transverse momentum, so 8 TMD PDFs that depend on X, the BureauConnects, the transverse momentum of the quark, and also of an interesting object which is called the gauge link. I believe you heard something about gauge links, probably from Jian Wei in the introduction of QCD part. So this slide is again something that we will address more in detail in the coming lectures, but we're gonna see what the geometric meaning of this gauge link is, namely what is the role of this gauge link in field theory and what are the physical consequences. Very deep, I have to say.
Excuse me, Andrea.
Yes.
Can I make you a little question? You've said that there is a universality property for this PDF.
Yes.
But I'm wondering if you can put the definition in the previous slide, please.
This one?
Yeah. Yeah. Here there is not the, I mean, it is not explicitly written that it is the Fourier transform with the state of the proton. How is it going to be universal if it has the dependence on the hadron?
No, I mean, okay, sure. So P here is momentum P. It's not like a proton or it doesn't mean it's a proton. It can be a neutron as well. But so if you measure something, say if you measure this correlator, this operator, or the distribution functions that are associated with it for a proton, then the information that you get about that proton in deep inelastic scattering has to be universal, in the sense that has to match what you get from measuring the same hadronic structure property, for example, from deep inelastic scattering.
Okay, okay, thanks.
Okay, but we're gonna see a few things about universality for PDFs and for TMDs. I mean, I can already tell you TMDs are non-universal, which is potentially a disaster, because I just told you that, okay, they have to be universal, but the non-universality can be calculated. So we recover a good situation, but we'll see more in that direction later on. So before going to like the more technical part of the talk, I want to tell you, please beyond, I mean, on top of listening to me, you should actually check out references. At least in my personal story, this is how I benefited from the knowledge of many different people by reading what they took the time to write down. So there is a very nice page on the HUGS website, the HUGS pedagogical page. I believe Alberto and the other organizers already told you to have a look at it. And for us, the 3D structure of the nucleon section is pretty important. You have some hyperlinks to some papers, lecture notes, and so on and so forth. Let me tell you what are my favorite ones. So lecture notes by Barone, Bacchetta, Jaffe, and Mulders. These 4 ones are pretty useful and pretty interesting. I think the most, okay, for example, the first one is the more introductory one, whereas Jaffe's ones are more advanced. So I would keep Jaffe's one like for later if you're not familiar with the topic, or if you already have some background, you can really learn some cool stuff from those lecture notes. Also books. So again, I believe these 4 books are very important for what we're gonna discuss in these days. So the one on the right side here, deep elastic scattering, is more introductory, and it's I think it's a very good starting point. The most advanced one is John Collins' book. It's very deep, very informative, but again, you might not read something else before jumping into it. And also the other 2 books are very nice. Muta's book is very useful for some calculations that we're going to address in the last part, in the other part of the lectures today. Because they have detailed calculations about the operator product expansion. Again, papers, I'm not going to tell you like what these papers are. I leave you the surprise. They are very nice. And if you have like, if your taste is more towards experimental things, I recommend you these 2 white papers about the 12 GeV operated Jefferson Lab and the physics of the electron collider. You can find many interesting things, but most importantly, you can find also many information about the physics of transverse momentum distributions and what can be measured and learned with these 2 wonderful machines. Okay, so in these lectures, we are gonna talk about DIS and partons and how to go from DIS to CDIS. More or less, this is what we're gonna discuss today. In the other parts of the week, we're gonna talk about properties of TMDs, evolution and matching, and so on and so forth, and how to do phenomenology. And also I'm gonna tell you something about open research directions. Okay, so DIS and partons. But I see it's like, I don't know, it's almost 10 to 5. I don't know if you wanna take a break now, or if we should go on for other 10 minutes, for example, and we stop later. Alberto and the organizers, what do you think?
I was thinking that you could go maybe until 11 here, like 10 minutes more.
Yes.
We open 5 minutes for questions, and then we take the break that is 20 minutes. But
okay. Okay.
If you think that is a good point now to stop, I mean, at this point.
No, let me go on for 10 more minutes. I think it's good, so that in the break you can think about what I'm gonna say now.
Okay.
Okay, so I believe you saw this experiment also at the beginning of the DVCS lectures. So I'm not gonna go into the details here, but at the beginning of the 20th century, this Rutherford, together with the 2 PhD students, Geiger and Marsden, they actually performed a very interesting experiments, game-changing for the history of science, where they discovered basically the atomic nucleus. So in the 60s and the 70s, people at MIT and at SLAC in the United States, they performed a similar experiment, but on a smaller scale. They scattered electrons of protons in order to test the substructure of these protons, or of hadrons in general. And from these deep inelastic scattering experiments, there was the first evidence that protons are not, I mean, made of jelly, but they are built out of they are built out what seems to behave like 3 point-like spin 1/2 constituents that they name partons. So there was a very interesting information that in the high Q square, in the deep inelastic regime, the photon exchanged by the electron scatters of something that seems to be elementary and seems to be a fermion and free. This feature was explained like with QCD later on, but they didn't know about QCD yet. So this is the starting point of our discussion. So you can think about deep inelastic scattering identifying the lepton plane, so the plane generated by the incoming and outgoing leptons in the following way, where the photon scatters off a hadron, a nucleon, or anything else, which is depicted here in the rest frame of the nucleon. And so you measure nothing in the final state apart from the scattered electron. So you don't measure hadrons. You just have a bunch of stuff that comes from the breaking of the target, but you don't really identify specific hadrons like a pion or a kaon or anything else. So in order to work out the formalism, it's useful to introduce what are called the light cone variables. So among the references I pointed out before, there is a paper by John Collins, an introductory paper, which specifically talks about light cone variables and why we use them. So I invite you to read it. It's pretty short, but it's really nice. It sets out the basic ingredients. So a specific vector can be represented with like the Minkowski coordinates 0, 1, 2, and 3, or the light cone coordinates that are basically a combination of the standard coordinates for a vector. And it allows you to view what happens, like the behavior of the vector compared to n plus and n minus, which are the basis of this light cone system. And these two vectors are called, this choice of basis is called the light cone variables, light cone basis, because n plus and n minus, they lie on the light cone. Namely, they are, the norm is 0 and their dot product is 1, so they are orthogonal. So keep in mind that this is the way you calculate the plus and minus component, and this is the way you identify the norm of the vector with light cone components. So because if you're going to work out some of the calculations in these slides later on, or if you want to think about what I said later on and try to think about pieces of the calculations, you need the light cone coordinates. So you also need to learn what the transverse metric is, and this is precisely the definition. G mu nu is the metric of your Minkowski space, and GT mu nu means that you're basically calculating the scalar product in the transverse space, so in the plane which is transverse to n plus and n minus. And the other object here is the antisymmetric projector. These two guys are used to, they show up quite often in the calculations, and we're gonna learn how to use them in the recitation sessions, most probably. So, okay, let's think about the kinematics for deep inelastic scattering. We have 4 external vectors at our disposal. We have the spin of your targets, if you're talking about a polarized, means a particle with a spin, not a pion or anything else without a spin. You have the momentum P of the target, the momentum L of the lepton incoming, and the momentum L prime of the outgoing lepton. You can build the following invariants: the energy in the center of mass S, the energy in the center of mass W square of the photon target system, Q square, that's it's the negative of the norm of the exchanged virtual photon, that basically tells you it's the resolution at which you're you're exploring your targets. And the variables here are X Bjorkin and Y. X Bjorkin is what we were talking about before, and is basically the variable that you can measure that corresponds to the collinear momentum fraction of the quark that you're going to study later on in the phenomenological part. So what is called the deep inelastic regime, or the Bjorkin limit, is the following. You keep X fixed, so you have to fix X. And Q square and the dot product of the hadron momentum and the photon momentum, they have to be very high. So in practice, they have to be much larger than m square, where m square is the mass of your target. So I told you that your target can have a spin, but what does it mean? It's not, the spin is like, it's not a normal vector like a momentum, right? It's like, it's more of an intrinsic property of your particle. So in quantum mechanics, I describe the spin by means of a density operator rho, which is a matrix in the standard quantum mechanical way of dealing with it. So if you're talking about this particle with a spin j, in order to describe the spin, you need up to, you need tensors with rank up to 2j. So let's make a simple example. If you have a spin 1/2 particle, like a proton or a neutron, you need a rank 1 tensor. A rank 1 tensor is a tensor with an index only, so it's a vector, it's a spin vector. So let's look at the example, which is much easier. So in order to describe the density operator here, rho, you can work out the following representation, where 1 is the identity operator, the sigma I are the Pauli matrices, and S is your spin free vector. So the 3 components of the spin vector are ST and SL. So we choose the longitudinal direction to be Z here. So the longitudinal spin component will be aligned with Z, and STX and STY are the 2 components of ST in the plane identified by X and Y. So in the rest of the talk, when you're gonna hear about transverse spin, keep in mind that this is what we're talking about. It's a vector that we need to define the density operator for the spin of the particle that we're talking about, and that the transverse spin has component in the X, Y, or 1 and 2 directions. So this is what happens for a spin 1/2. But according to you, what happens if we have a spin 1? According to what's written on this slide, what happens? Anyone who feels like telling me? You do have the slides uploaded on Indigo, so you could also look there. But tell me what happens if I have spin 1 instead of spin 1/2. How many objects do I need in order to generalize this formula here?
You would need a rank 2 tensor.
We need a rank 2 tensor. That's correct. Because 2j, if j is 1, I need a rank 2 tensor. A rank 2 tensor is a matrix. So this is what we get. So in order to deal with a spin 1 particle, you have the identity operator, sigma, capital sigma I are a generalization of the Pauli matrices, and sigma ij are linear combination of the Pauli matrices again. And most importantly, we have S, which is again the spin vector for the spin 1 particle, and T, which is the spin matrix for the spin 1 particle. So again, you have a spin vector and a matrix of objects, which are called the tensor polarization degrees of freedom for the spin 1. I'm telling you this because I believe in the, this week you're gonna hear about the physics of light polarized ions, and you might also hear about deuteron, the physics of polarized deuteron. So from the theory point of view, this is how you introduce spin 1 effects on top of spin 1/2 effects. This is the difference that you get when you talk about spin 1 versus spin 2. So this is the recap. For spin 1/2, you have a vector. For spin 1, you have a vector and a tensor parameterizing your degrees of freedom. So a polarized deuteron has more degrees of freedom compared to a proton. There are more, it's more difficult, but more interesting to study. Let's put it this way. So let's now focus on the cross-section for deep inelastic scattering. So the cross-section can be calculated as the contraction of a leptonic tensor L mu nu and a hadronic tensor W mu nu. The leptonic part of the leptonic tensor basically deals with, it's trivial to say, but the leptons in the process. Whereas the hadronic tensor deals with whatever is connected by, with whatever is related to the hadron part. And the two, are multiplied by a prefactor, which is also related to the propagator for these 2 photons here. So, I mean, probably you're used to seeing Feynman diagrams to describe processes. This is a different thing. It's not a Feynman diagram, it's a cut diagram, which is basically the squared of a Feynman diagram of Feynman diagrams. So the left part of the diagram with respect to the dashed line is a Feynman amplitude itself, whereas the one on the right-hand side is the conjugate, the complex conjugate of the Feynman amplitude in this case. And the dashed line is the so-called cut, and it means that whatever is crossing the cut is a real particle, so it goes into the final state. So here, for example, we have the lepton L prime is crossing the cut, so it's going to the final state, it's a real particle. And also here, whatever is in the blob that we don't know because it's hadronic non-perturbative stuff is crossing the cut. So it means that in our detector, we're gonna have a bunch of hadronic stuff that we have to know how to classify. Okay, so this is a pictorial representation of what I told you. The leptonic tensor is the yellow blob and the yellow formula L mu nu. We can calculate it because we can use QED, and QED in the regime that we are dealing with is perturbative. The hadronic part is the green one. And it's not completely calculable because we are dealing with QCD at hadronic scale. So we're going to have a mixture of perturbative and non-perturbative QCD. Okay. The hadronic tensor itself, if we want to focus on this part only, can be calculated as the product of two matrix elements. And let's have a look at this formula and then we stop for a moment. So let's focus on the brackets here, the last part of the formula. You have a state with momentum P, which in the diagram corresponds to the arrow here that I'm pointing to here. You have an operator J that acts on the hadron with momentum P. And out of this action, you have Px, namely, which is the gray blob, the remnant. So it means that you're acting with a current on your proton and you're generating something else of hadronic nature. This current is basically the electromagnetic current inside of the target, inside of the proton. So you have two fermion fields, psi bar and psi with gamma mu. Okay, this is the standard form for an electromagnetic current in QED. And if you think about it, this is what happens is the following. So you have an electron which has been shot towards your target, and the electron, since it's charged, feels this electromagnetic current inside of the proton, and they do interact by exchanging a photon. And this has a lot of consequences, and if you want, I can stop here.
Well, we can go for
we can go forward. Sorry, I was stopping because you told me to stop around 11.
No, I was meaning maybe we can take like no more than 5 more minutes for if there are final questions of this session, and then we take the break. Is that okay to you?
Okay, so shall I go on, Juan?
No, I mean that it's a good point to stop.
Okay, sorry, I didn't get it.
For like 5 more minutes and then take the break.
Yes, please.
So we have a raised hand by Andrew Dodson. Go ahead, Andrew.
Yeah, I have a quick one. So on slide 37, when you define the contractions of these tensors to get your densities, are these tensors under just rotation since they're Latin indices?
Sorry, can you repeat the last part of the question?
Yeah,
are these tensors?
Are these only tensors under rotation, or are they full Lorentz tensors since they just carry Latin indices?
Sorry, which kind of indexes?
Latin, the IJ instead of like mu nu.
No, these are IJ. So so these are the same indexes of the Pauli matrices. So it's not the full mu nu Lorentz. So it's a tensor under rotations, I would say.
Okay.
And by the way, yeah, go ahead.
Oh, I'll let you finish. Go ahead.
So I wanted to say that you can actually get a pictorial representation of this matrix as well if you have a look Did I? Okay, on the paper I linked here at the beginning of the slide. So this is the paper where they studied the spin-1 effects inside of a deuteron for parton distribution functions. And in one of the appendices, they have a very nice graphical interpretation of this, the components of these tensors here in terms of the orientation along this direction, X, Y, and Z.
Awesome. And then my only last quick thing is, with regard to TMD physics, I've heard reference to these Nachman variables before. I was wondering if you would talk about those at all.
We can talk about it, sure. Not today though. It's something that fits more into the phenomenology part.
Cool. Right,
but sure,
you.
I mean, we're gonna talk about the difference between X-Birkin, X-Nachman, and what the implications are. Sure, that's a good point.
Thank you.
Thank you, Andrew. Now we have a raised hand by Patricia. Go ahead, Patricia.
Yeah, okay. Thank you for the very nice talk. I was also wondering about this spin that is described by a density operator. I would like to know in what way does this affect the description of the cross-section that you have started right now? Like, in what way, what's the connection?
Yeah, you're gonna see that like in the next slides.
Okay, then.
But, yeah, but basically I can tell you, when you decompose the hadron tensor in terms of Lorentz structures, when you can basically, when you think about all the possibilities in terms of polarizations that you have in your cross-section or in your hadronic tensor, you do get additional terms for the spin-1 case because you have more structures to play with, basically.
Okay, thank you so much.
You're welcome.
Thank you, Patricia. Now we have another question by Victor. Go ahead, Victor, please.
Yeah, sorry for going back to this universality thing, but I believe
sure.
But I believe it is fundamental. And you said that these states are states of momentum. But taking into account that all these parton distribution functions, GPDs, and so on are obtaining through elements of the scattering matrix, in those elements are taken with the states, for example, of the proton. And so at the end, you have these momentum states, but of the proton. Let me explain myself. If you have a proton with this particular momentum, you could write this state as a weird, complicated superposition of annihilation and creation operators of gluons and quarks acting over some vacuum. But and that could give you, I mean, that superposition of creation and annihilation operators could be such that at the end you have some state of precise momentum. But in the case, if you would be changing, for example, from a proton to a neutron or I don't know, an eta or any other hadron, for the same momentum, you would have for the same momentum state, you would have a different combination of these annihilation and creation operators. Therefore, this matrix element that defines the PTF or the GPD or whatever may be different. So I don't.
No, but yeah. So you're right, but it's correct that what you get for a proton is different with respect to what you get for a neutron or another hadron. What I mean, because I mean those are different particles, so their structure in terms of quark and gluons has to be different. But what I meant is that considering a specific hadron, like a proton with a specific momentum, that information has to be the same if you get it from Drell-Yan or if you get it from deep elastic scattering.
Yeah, but what I'm trying to stress is that that's only a belief, because if you take a look onto the PDF, the formula that you showed, those P states are associated clearly to the hadron that you are working with. And if the structure of this hadron is different, even if, I mean, you could do the same for different hadrons with the same matrix element, but these different hadrons have a different structure, therefore a different combination of these annihilation and creation operators. Therefore, at the end, you could have different PDFs, despite we are assuming universality. So my problem is that taking into account that the matrix elements could be different because of the different composite structure of the hadrons you are working with, what I don't see is why people believe so blindly on universality, because I don't see it. I mean, you can just take a look onto the formula and you see that universality may not be true.
So I can tell you, I can give you like a very practical example. I mean, it's not a blind belief, I would say. So if we are not able to define something universal, I think we are failing at the very beginning, because we are not studying. So the proton is the proton, right? So there has to be, I think, something characteristics of it, something very peculiar of it, sorry. It cannot be that a hadron, if you observe a hadron with a specific process, you get something different than observing it with another one. And I mean, people observe this, I think, when they fit, for example, the parton distribution functions with a specific data set. For example, if you fit the parton distribution function with the REYES data, then you're able to compute predictions for other kind of experiments. And that works. It's not that it doesn't work, it works. So that means that we're actually extracting something universal from our data. But I think it's a very interesting discussion, and I would like to understand better, a little bit better your concern and your point of view in order to give you like a more proper answer. Maybe we can talk a bit later also, if you want.
Yeah, for sure. Okay, so then we postpone it.
Yeah, so that you also have the chance to tell me a bit more in detail what your concern is.
I mean, the idea is pretty simple. Instead of having, can you show the PDF, please?
No, but sorry, I have quite a lot of material to show you today. So I believe it's better if we do it later, if you don't mind.
Sure, no problem. Thank you.
Thank you, Victor.
Well, if there is no more questions, it's a good point to take a break. Thank you everybody for coming, and see you in about 15 minutes.
Okay, 15 minutes, okay.
It's 11:25. We start back.
25, okay, 12 minutes.
Yeah.
Hi, everyone. Are we back?
Andrea, I'm here. Juan, are you there? I don't see Juan.
I'm here. Yes,
Okay. So, take over.
So, welcome back to Andrea's second lecture. Just a quick reminder.
I cannot hear it. Well, can you hear me or not?
Yes, I can. Can you hear me? Hello? Can you hear me?
I can hear you.
I have a problem with my headset, sorry.
Oh, Juan, I can hear you.
Let's just see if you can get a headset working.
Yeah, looks like the issue is the
No, but I cannot hear you, so.
Let me see if I can reach him in the chat.
Yeah, he's already writing that it's already headset. So
What about now? Can you try to talk, please?
Test 1 2 1 2. Can you hear us?
Can you hear us?
What's going on?
Can you hear us now? 1 2 3.
Hello?
Hello? 1 2.
Hello? Can you hear us, Andrea?
okay, let's wait a little bit while he reconnects. Here he is. Can you hear us, Andrea?
All right, can you hear me?
Yes.
Oh, great, I can hear you very well.
Perfect.
Perfect. So we're back to business. So, well, you can share screen, Andrea, and come back to the lecture.
Okay, now I am able to share the screen. Sorry for this. Okay. So where were we? Okay, you can hear me well, right?
Yes.
Everything is fine. Okay, so back to the hadronic tensor. So we stopped before the break saying that this is the expression for the hadronic tensor. That physically means that the lepton feels the electromagnetic current flowing inside of your target, and they exchange a photon because of that. So since we are talking about exchanging a photon, this is the form of the current. If you had weak interaction and exchanging a W or Z boson, the expression of the current would be different. We would be getting different things in the following. But okay, let's now work with a photon. And since the hadronic tensor is a non-perturbative object, what we can do is to try to parameterize it. And the objects we know are the kinematical objects, so the momenta of the target, the momentum of the photon, and the symmetric tensors that we can build with it. Now we are talking about the unpolarized case. If you had a polarized hadrons, you would have in this parameterization also the spin vector for a spin 1/2 particle or the spin tensor for a spin 1 hadron. So you can take this formula here where A, B, C, and D are just coefficients of this expansion on symmetric tensors. You can shake it by mixing it with parity invariance, the time reversal symmetry of QCD, and the gauge invariance, and also hermiticity conditions. And what you get are the so-called structure functions parameterizing the hadronic tensor. Let me stress again, I mean, here we are talking about electromagnetic interaction. With weak interaction, you don't have parity as a constraint, so you would get another structure, as well as for spin, that you would get different structures. But as I said, if you combine that expression with the symmetries of QCD, you get two structure functions in the unpolarized case, F1 and F2. Which are many of you probably have heard about the structure functions, the unpolarized DIS structure functions. So these two structure functions, F1 and F2, can be recast in terms of other two structure functions, Ft or UUT and FUUL, that are basically a combination of F1 and F2 by simply changing the basis for this expansion. So if you choose a basis that's defined below here with the Q or Z and T vectors that are space-like and time-like vectors, you can actually expand your tensor on Ft and Fl, the two structure functions. Then, I mean, the reason you might want to do this is that these two structure functions are linked specifically with the polarization of the exchanged photon. So FUUT means that this is the structure function that it's related to the first U means it's an unpolarized lepton scattering off an unpolarized target, exchanging a photon with a T, a transverse polarization. And the same thing holds true for the other structure function, but you have a longitudinal polarization for the exchange photon. So as I said, F1 and F2 are the standard unpolarized structure function, which are related to Ft and Fl. The change of basis is just for making more explicit what the contributions of different photon polarizations are. So if you have a polarized particle instead, what happens? You have additional structure functions on top of Ft, FUUT, and FUUL. You have FLL and FLT cos phi. So the FLL structure function is related to the longitudinal polarization of your target. So again, the first subscript is for the polarization of the beam, the lepton beam, and the second one for the target. So you have a longitudinally polarized beam scattering on a longitudinally polarized target. In the other case, you have a longitudinally polarized beam scattering of a longitudinally polarized target. Yes?
Excuse me, we have a question in the chat.
Yes.
Here from Murchana Roy, she asking, why only two structure functions? Can there be more?
In the unpolarized case?
Yes.
So in the, I mean, no, there cannot be more if you work with I mean, if you exchange a photon and if you assume the symmetries of QCD. So we started with the A, B, and C, D functions because this is the most general combination of the vectors that you can build. And then if you work with the symmetries of QCD plus the hermiticity of this tensor here, then only two functions survive. If you have weak interaction, they are free. If you have spin, you are more, but unpolarized and electromagnetic interaction, you only have two.
Okay, and there is another question by Patricia in the chat.
Yeah.
Is this parameterization related to the Gordon decomposition? I guess that she refers in the polarized one.
I don't remember exactly the detail, but we can have a look later, Patricia. Is that okay?
Yes, of course.
Okay, thank you.
Thank you, guys.
Okay, so again, so if you have a polarized case with spin 1/2, you get two more structure functions, these two, longitudinal and transverse, and which are related to G1 and G2 structure functions that you might see in other papers or lecture notes. Something interesting to notice here is that you don't have a structure function that starts with a T subscript. So you don't have a contribution from transverse lepton polarization, which in principle might be there, but the only thing is that it comes from a part of the leptonic tensor that it's proportional to the lepton mass. So since we are working with an electron here, we basically neglect that term because it's suppressed by the electron mass, which is almost zero. If you had a mu1, maybe it would be like more sizable, but in our case, it does not contribute. So that's the reason why you don't get structure functions with a T subscript for the lepton. This is what Patricia asked before. Instead, if you have a spin 1, you have 4 additional structure functions, B1, B2, B3, and B4, which are related to each other. They are not all independent, but they are essentially due to the presence of the T mu nu matrix in the decomposition of the hadronic tensors. So instead of having SL and S transverse here, you would have combinations of these matrices with the tensor polarization. So for the deuteron, there is more physics that we can study, but it's also more difficult to study because experimentally the tensor polarizations are pretty difficult to handle. And I believe Elena along in the coming lectures she might tell you something about it. Okay, so back to the cross-section. Remember that the cross-section is a contraction of the leptonic tensor and the hadronic tensor. I didn't give you here the expression for the leptonic tensor, but I mean, you can find it in the lecture notes that I pointed out in the beginning, for example. But I mean, it's not the interesting part of the lectures. If you contract these two tensors, so the 4 structure functions I introduced previously emerge, the FT, FL, and the FLL, and the transverse one. Yes, one?
We have another raised hand by Art. Go ahead.
Hi. So on the previous slide, so you were telling if we have a muon instead of electron, then we will have more structure function. So in that way, it depends upon the probe, like.
Yeah. I mean, if you're scattering a lepton which is massive, I mean, you have additional terms because you have additional structure functions because you have additional terms in the leptonic tensor.
So what does those structure function tell us about? Like,
so those structure functions would be related to probing a target with a transversely polarized lepton beam. I have to say I've never seen them written down in the literature, maybe because they're very difficult to handle also from the experimental point of view. So I cannot tell you more about it. I can only tell you that in principle, we are neglecting the lepton mass. So we are missing something. This is reasonable because this is mainly done with electrons, or at least our description is done in terms of electrons. So we are not missing anything in principle because the lepton mass is negligible compared to the other scales.
Okay.
Yeah, I will have to think hard in order to find a paper with those contributions written down. I think I've never seen them, but it might be like my ignorance. I don't know.
Andrea, I can send around a reference. I will look at it and put it in chat.
Okay, you see, it's my ignorance. Alberto knows more about it.
We have another raised hand by Murshana.
So you're saying that we are ignoring the lepton mass, right?
Yes.
So if there was like massive particle, then the other structure functions will be mass dependent. Is that like?
No, so the mass will not enter in the structure functions themselves. So the mass will appear as a coefficient of the structure function, like for example, the SL here.
Okay.
And we have another question in the chat. Patricia is asking, the additional structures due to the tensor polarization in slide 44 depend on B1, B2, B3, B4. But can you repeat what are those variables there?
So B1, B2, B3, B4, these are just the names of the structure functions like FLL or FUUT. I didn't write down the expression completely because it's pretty lengthy, but you would have, for example, something, for example, a component of the T-mu tensor multiplied by B1, another component multiplied by B2, and so on and so forth, something like that. If you are interested, I can give you the references where those calculations are carried out.
Okay. No more.
Okay. No more questions. Okay, then I can go on.
Go on.
Okay, so I was repeating what the cross section looks like. You have 4 structure functions for a polarized nucleon, and the structure functions here are just functions of x, which is, I mean, up to now corresponds to x per keen, and the q square or q, so the resolution at which you're studying your hadron. Again, for a summary, I invite you to look at the paper linked here at the bottom of the slide, where they have a comprehensive description of the things I'm telling you today. But again, so up to now, we didn't see any quark or gluon in the description of this hadronic tensor, which is a bit disappointing because we would like to study Parton distribution functions and TMD Parton distribution functions. So our goal now is to understand how we connect this organization of the cross-section, which is based on the symmetries of the theory and on the vectors that we can use, with Partonic interpretations of hadron structure and hadron formation. In order to do this, we have to, we will do it for DIS, first of all. For other processes, there are other ways. So I want to do it with DIS because it's, I mean, it's a process for which there is a powerful mathematical tool at our disposal. The first thing we have to remind ourselves is the following. So if we think about this expression of the hadronic tensor, namely the hadronic tensor written in terms of the the electromagnetic currents, we can see that by using the properties of the delta, so the Fourier, basically the Fourier decomposition of the delta function, the delta distribution, the completeness relation for the intermediate states here, which are just the remnants of your target when it's after being hit by the probe, and using the translational invariance of the currents, we can recast the hadronic tensor as a matrix element of a commutator of the two currents. And this is pretty important. I mean, it might seem like a mathematical detail, but there is a lot of physics in this. So because we are dealing with a commutator and the two operators are, the operator is non-local, so the separation is between 0 and psi. Causality implies that psi square has to be positive. This means that if 0 and psi, if psi is outside of the light cone centered in 0, if you act first with J and then with J dagger, that's the same thing as doing J and then J dagger and, sorry, I said it wrong. So mathematically, the two operators, they commute because there is no interaction between what's outside of the light cone, right? So if you have J dagger and J, that's the same thing as having J and J dagger. So psi square has to be positive. Then the so-called Riemann-Lebesgue theorem or lemma implies that the hadronic tensor is 0 unless psi plus goes to 0 in the deep inelastic limit. So this poses a constraint on the hadronic tensor, a pretty powerful one, namely that the hadronic tensor is dominated by what happens on the light cone. So when psi square is equal to 0. Think about, this is a little calculation where you need to keep in mind how the dot product of two vectors with the light cone coordinate works. If you have psi square to be positive and psi plus goes to 0, that means that psi square has to be close to 0. And for this reason, we can use the operator product expansion on this operator. So the operator product expansion is, in a nutshell, this equality. Namely, if you have the product of two operators, A and B, you can rewrite this product as a series of coefficients C times operator, O. And this only works when the difference is small, between X and Y is small. So it can be, for example, our case for the hadronic tensor, because the separation is almost 0. The lower is the value of n, the more dominant is the contribution. So as I said, thanks to the light condominance, we can apply this technique to the hadronic tensor. And what happens is the following. So actually, the expression of J is what the electromagnetic current is what allows us to make a connection with partonic degrees of freedom, because J contains the quark fields, psi and psi bar. So if you insert the expression of J in the commutator here, and you apply the operator product expansion, you can basically decompose the hadronic tensor in the sum of these 3 contributions. I'm not going to work out the details here because it's pretty long, but I invite you to check Muta's book for the details. There is an entire chapter on the operator product expansion, and the calculation is carried out in detail. So it's very instructive if you want to spend a couple of hours on that. I really recommend it. So the first contribution basically sees the photon producing a polarization of the vacuum and then going away. Okay, it does not interact with your hadron. So the lower blob represents the targets before and after the interaction. So here, this is a so-called disconnected diagram. There is no interaction between like the upper part and the lower part, and we're gonna neglect it. It's irrelevant because by definition in the hadronic tensor, I didn't specify that, but by definition, you only have connected diagrams contributed to it. So this is the lowest order. In principle, it's like the bigger term, but it's irrelevant. It doesn't contribute. Then you have a diagram of this type where you have the photon coupling with a quark, which is extracted from the proton by means of the operator psi. It interacts with the photon, it goes to the final state, crossing the cut, and then in the conjugate amplitude is reabsorbed into the proton. This is basically, you can see that happening if you insert, as I said before, the psi and psi bar operators in this expression here. So this is the dominant contribution, and then we also have another one, a more complicated diagram where you have 4 fermionic legs interacting with the photon, being extracted and reinserted into your target. This is the so-called cat ears diagram. It definitely contributes to the hadronic tensor of the deep elastic scattering, but it's suppressed with respect to the central one. So this is one of the so-called higher twist contributions to the hadronic tensor, and we are not going to focus on those ones for now. So just to recap, the dominant contribution, if you apply the operator product expansion to the hadronic tensor, is this one, where you can see the hadronic tensor has an extraction of a quark from the proton by means of an operator psi, and the reinsertion of the quark into the final state hadron in the complex conjugate amplitude. So again, if you work out the math completely, you see that the hadronic tensor can be written as the trace of a correlation function x and a correlation function phi, which is a function of x, and the spin of the target, traced with some other Dirac matrices. So here the neat thing is the following. So the variable that you're measuring experimentally is x per keen. And from the kinematics of deep elastic scattering, you see that it matches this x variable here, which is defined to be the ratio between the light plus component of the quark divided by the one of the hadron. So you really have a connection between something that you measure, which is x per keen, and something that's by definition related to the collinear, to the parton dynamics. And in particular, this x here is the fraction of the hadron momentum carried out by the quark. So this should tell you that there is a meaning, a deep meaning of for x per keen in terms of the collinear parton, the collinear quark dynamics. And another important thing here is to notice from the formula is that the quark transverse momentum is integrated out. You don't see quark transverse momentum here. That's why, I mean, as a result, that's why you don't have transverse momentum distributions or transverse sensitivity to transverse momentum in inclusive deep elastic scattering. Okay, so let's recap. Let's recap for a second. The operator that you can define by using the operator product expansion is this kind of
We have another question.
Yes.
Can you explain a bit more why we can do that approximation? Epsilon can approximately equal to X.
Yeah, I know. I mean, I presented it here without explaining that too much. It's okay. It's something that we can see like in the phenomenology section. I'll tell you more about it when we talk about X-Nachtmann as well, for example. For now, I mean, if I think about what I wanted to tell you today, please be satisfied with this for the moment. Just keep in mind that, just keep in mind that what you measure, X-Bjorkin, corresponds to something which is related to collinear parton dynamics.
Okay, thank you. I'm sorry for making so many questions. It's just that it's very interesting.
It's fine.
Andrea, a very quick thing that might satisfy everybody until you come to that is that this approximate sign is valid at first order in the m square over q square expansion. So at first order in m square over q square is the mass of the target. So if q square is large enough, you can neglect the mass of the target, and this equal sign is correct in that limit.
Yeah. So yeah, I mean, if you take the expression, as Alberto said, if you take the expression of k plus, you compute it, and you neglect those terms that he was talking about, then we get an exact equal sign between X and X-Bjorkin.
I mean, if you allow me, I made this computation just to give Patricia an insight. And the point is that you have in the middle between the two photons, you have a propagator, and that propagator can be separated on some principal value and a delta. And that delta is, at the end, you can simplify it and give you xb minus x.
Yeah, correct. Yeah, so you see there are many, not many, but there are a few ways to explain this equality, and this is certainly one of it. Okay, should I go on?
Yes.
Okay, so let me define the object that you can get from the operator product expansion, which is this matrix here, dependent on K, the momentum of the work extracted from the proton, and P and S, which are the momentum and the spin of your proton, because we're talking about a spin one-half particle now. Okay, so this is the general matrix, the full matrix. What shows up in the DIS hadronic tensor, in the DIS cross-section, is phi as a function of X, if we talk about the partonic variables. Namely, the object here on the top of the slide integrated on the momentum components, integrated over the transverse momentum component, especially, so you don't have any sensitivity on transverse momentum here. And the integration of K plus fixes basically X to be the ratio between K plus and P plus. And it's important to notice that the separation between the two points in this correlation function is exactly on the light cone, and it's on the along the minus direction. So parton physics is really on the light cone, as we saw previously working out the light cone dominance feature for the hadronic tensor in DIS. Okay, so again, this correlation function here, phi of K, P, and S, it's a bilocal matrix element, and we don't know that much about it from the QCD point of view at lower energies, at the hadronic scales. So it's a non-perturbative matrix. It's a non-perturbative object, and we can actually. So okay, so I spoiled my sentence. We can do this. We can use the same argument that we used for the hadronic tensor. It's a non-perturbative function. We don't know how to calculate it, so let's parameterize it in terms of structures that we know. And in particular, let's parameterize it in terms of the vectors that we have, like the parton momentum, the hadron spin, or the tensor polarization. And what we get after combining these parameterizations with the symmetries of QCD is the following. So the collinear correlation function can be parameterized with up to 4 collinear parton distribution functions at leading twist. You have f1 of x, which is the unpolarized parton distribution function, g1 of x, which is the longitudinally polarized PDF or the elicited PDF, h1 of x, the transversity parton distribution function, namely the probability of finding a quark with transverse polarization inside the transversely polarized hadron. And then you also have an additional PDF for the tensor polarization. You see that here we have one of the components of the T matrix. You have SLL. So you have this parton distribution function here, which is the only tensor polarized PDF that survives all the constraints from the symmetry of QCD at the collinear level. So take home message, we have 4 PDFs at leading twist at the collinear level when we do deep elastic scattering, when we study deep elastic scattering. And yeah, so in the interest of time, I wanted to tell you something about what actually we know about these collinear PDFs, but I might skip these because, I mean, you probably know already something about it. I wanted to tell you something about the impact studies from the ESE as well, but I will move it to the last lecture. And let me finally ask you, okay, so I hope you liked what I told you so far today, but the question is, what about transverse momentum? So we are talking about transverse momentum imaging, and we saw no transverse momentum up to now. So what is the problem? The problem is that we are looking at the wrong process if we want to learn something about transverse momentum. DIS is very nice because it allows you to define all the ingredients needed to work with PDFs, hadronic tensor, the operator product expansion, and blah, blah, blah. But it's not the most useful process if you want to talk about TMDs. So again, what is transverse momentum? Let's go back to this slide where we had the hadronic tensor for DIS, where we saw that where we wrote that the quark transverse momentum is integrated out. So the reason is that inclusive DIS is differential in X-Bjorken only. So you see, if you have the cross-section for DIS, that's differential in X-Bjorken and no other variables related to the parton dynamics. So you need to have something with an experimental handle on transverse momentum. For example, this is not the only process that we can consider, but it's one of the nicest ones. Let's consider semi-inclusive deep elastic scattering. What does it mean? It means that on top of detecting a lepton in the final state, we also detect a hadron. So it's semi-inclusive because we are choosing a specific hadron coming from the struck quark. So this was the situation for deep elastic scattering, where you measure only the lepton. Instead, this is semi-inclusive deep elastic scattering. So you have an additional hadron in the final state. But very important, on top of detecting this hadron, if you want to have sensitivity to transverse momentum, you have to measure the transverse momentum component of this hadron. So as we said in the previous slides, we have to have an experimental handle on transverse momentum. Again, for the details, I invite you to check the paper down here. So the cross-section for DIS versus the one of CDs. But sorry, how much time do we have?
About 30 minutes.
You have about 20 minutes, Andrea, still.
Okay, 20 minutes. Very good, very good.
You can go to 25 because there were some questions and some difficulties at the beginning.
Okay, okay.
Plus, time for questions. So.
Okay, so I think we will be able to make it. So the difference between DIS and CDs is the following. At the diagrammatic point of view, what changes is the hadronic tensor. The leptonic tensor is the same. At the hadronic tensor, you have a hadron. From the blob, you have you see a hadron represented by the diagonal dashed line, which is emerging from this non-perturbative blob, and it goes to the cut. So it means that it's going to the final state, the detector. So how do you describe it? Actually, the cross-section is more complicated because it's more informative. we have, so the green boxes represent a handle on collinear parton dynamics. So for DIS, we have X-Bjorkin. For CDs, you have X-Bjorkin and ZH. And ZH is defined here on the right-hand side of the slide, and it represents basically the fraction of the quark's energy, which is hadronizing, carried by the hadron that you're detecting. But we also have a handle on transverse parton dynamics because we are also differentiating pH perp. And as we saw from the previous slide, pH perp is the transverse momentum of the hadron in the final state. And we will see that we can give a description of this transverse momentum in terms of the quark transverse momentum, the one like in the hadron structure part and the one in the hadron formation or hadronization part. All right. Okay, so let's check again the hadronic tensor for semi-inclusive DIS. In inclusive DIS, we had 2 structure functions for the unpolarized case. In CDS, you have 5, and this is just because you have more vectors to play with. So we have an additional vector here, which is the momentum of the detected hadron. That's going to help us with building other structures. So eventually you have more structure functions in your hadronic tensor. It gets pretty complicated, but you will see that later. So these structure functions here emerge also, they show up also in the cross-section, of course, after contracting with the leptonic tensor. And these structure functions are a function of, again, X-Bjorkin, the Z hadron, the transverse momentum of the hadron, and the resolution of your process, which is Q square. Here is the hard scale of your process. And yeah, it's related to the invariant, it's the invariant mass of the photon that you are exchanging. If you consider a polarized target instead, so if you have a spin 1 particle, from 5 structure functions, we go to 18 structure functions. So it's much more complicated than inclusive DIS. You have many more terms, but these terms are interesting, of course. We should not be too worried about it. Let me tell you again that as for DIS, since the leptonic tensor didn't change, we don't have any, if you're working with an electron, you don't have any structure function which is proportional to the initiated by a transversely polarized lepton here. I mean, we have enough of 18 structure functions for now, I would say. So each of them represent a contribution to the cross-section. And I also want to tell you that if you consider a spin 1 target, not a spin 1 half particle, we don't know yet how many structure functions there are. So because no one had the patience and the time to sit down and do the full calculation yet. So I believe this is like an interesting research direction. If you're interested like in the properties of the polarized deuteron, and I believe it might be like an interesting one because of the current and the future experimental programs involving the deuteron. You might want to consider doing this. It's not a difficult exercise. It's just like you have to be very careful, and it takes some time, as everything in physics anyway. But okay, so apart from this, again, up to now, we don't have any partons in our description. And as we did for DIS, we have to understand how to connect the structure functions to parton distribution functions. So let's go back to the expression of the hadronic tensor, where you have 2 brackets where the operator is the electromagnetic current. So the problem here with respect to DIS is that because of the pH vector in the final state, you cannot use completeness here in the operator, and you cannot write the hadronic tensor as a commutator of the 2 currents. So there is no way to do it. Actually, you can only do it, I think, for deep elastic scattering and for a plus and minus annihilation inclusive. For other processes, you cannot do it. So you have to revert to something else. This something else that I'm telling you about now is the so-called diagrammatic approach. The diagrammatic approach basically teaches you how to write your hadronic tensor in terms of convolutions of correlation functions, and it reproduces the results from TMD factorization at lowest order in perturbation theory, of course, when there is a factorization theorem. So it's, I would say that like the younger people in the field now, or maybe the people interested in the more formal aspects, they immediately start with the TMD factorization approach, either like in the standard perturbative QCD or with soft collinear effective theory. These results match what you can do with the diagrammatic approach at the lowest order in perturbation theory. So they are compatible, these approaches. And what happens for semi-inclusive DIS is that this approach tells you that the hadronic tensor can be written in terms of a correlation function phi and a correlation function delta. The phi is exactly the same one that you have for inclusive deep elastic scattering, that tells you that it teaches you how to extract a quark from a specific hadron, and that quark then goes into the in the hard interaction with the photon. The other correlation function describes the hadronization part of the cross-section, namely the dynamical process by which your quark transforms into a hadron, and it's again a non-perturbative process. So that's why we are introducing a correlation function. As for the OPE, there are also higher twist terms which are suppressed, so we're not going to consider it now here. Okay, so how to reach the partonic interpretation? Basically, just by inserting the expression for the correlation functions that we defined before. We already know that the definition of the phi, and now we're going to have a look at the definition of the delta as well. So this C letter here that's written in the hadronic tensor is basically like a shorthand notation for a convolution of this form. The take-home message from this slide and also the previous one is that in semi-inclusive deep elastic scattering, what happens is that you're not integrating out the transverse momenta anymore. So you're left with PT, which is the transverse momentum of the quark from the target, and KT, which is the transverse momentum of the quark after the hard interaction that's hadronizing and going into the detector. And as you can see from the convolution formula here, the two transverse momenta PT and KT, they are convoluted together and they give you through the delta function the transverse momentum that you're measuring, pH perp. So this is really the connection between what you measure and what you can define at the partonic level. So that's why semi-inclusive DIS with sensitivity, where you measure the transverse momentum of a hadron, allows you to draw maps of hadron structure and hadron formation in momentum space. Okay, for clarity, I'm going to repeat here the definition of the quark distribution correlator. So the correlation, the non-perturbative correlation function that allows you to extract a quark from the hadron. That's the same object we saw before, phi. And the only difference is that we are not integrating over PT anymore. So, but PT is is a variable here now. And this results in having a non-locality, which is not on the light cone anymore, but has two components, minus component and transverse component. This is very important, I'm not going to tell you today why, but keep in mind that this is very important. Actually, it's very important for the universality properties of the particle distribution functions.
Excuse me.
Yes?
There is a question in the chat. Made by Luca, asking, how does the weight W work? Is it extracted or modeled? There is another raised hand.
Luca, you mean the W here in slide 73?
Yes.
The one in the convolution?
Yes, this one.
And so this W here, you will see it later, but it's a function of the transverse momenta, and that's basically what's going to give you the azimuthal dependence of the structure function, either a cos phi or a sin phi or whatever other dependence that you can have. So it's not a non-perturbative object. This is something that it's really kinematical.
Okay, understood. So you can extract by the kinematics of your specific process, basically.
Yeah, I mean, it's something related to the specific polarization for a certain process. For example, for C disk fully unpolarized, this W is omega factor is 1. For the Sieverts function, for the Sieverts structure function, sorry, you have something which is proportional to KT and the scalar product with the measured, the direction of the measured hadron. You're gonna see it in the next slides. It's really a kinematical factor.
Yeah, it's not something that you get from a fit or from a model.
No, exactly. One is right. It's not something that you have to fit. It's just a kinematical factor.
Okay, thank you. Because I saw it, but I never understood exactly how you calculate it. Okay, thank you.
You're welcome.
We have another raised hand by Arjun. Go ahead, Arjun.
So in the diagrammatic approach, we see that this incoming photon, this is connected to both the struck parton and the parton that we are which hadronize, and we are also detecting in the detector. But it does not necessarily it should be connected with the hadron which is going out. That we are detecting.
Unfortunately, sorry, I didn't hear you quite well. Can you repeat the question, please?
Yeah. So the incoming photon is connected to both, like the struck parton in the proton and one that we are detecting in the semi-inclusive DAs. Yeah. So in the diagrammatic approach, we see it is connected to both, but it is not necessarily connected to the outgoing hadron that is hadronizing.
I'm not sure I understood you completely, but so the photon, so basically the photon here is just, so the interaction between the photon and the incoming quark and the outgoing quark is just the lowest order approximation for this hard interaction. You have the quark which interacts with the photon, and then it goes to the final state. But I mean, this is the very lowest order contributions in your cross section. You can have more fancy things, but I mean, they're not going to modify like the lower and the upper blobs. They're factorized in the factorization, if you want to put it in the factorization language.
Okay, I understood. So that means like there can be additional diagrams, but at the leading order, this diagram contributes. Okay.
Yeah. So here, instead of instead of the photon coupling to the quark lines, you can put like I don't know, a small blob. And for the small blob, you mean like all the possible perturbative interactions that you can have, QED interactions that you can have.
All right, fine. Thank you.
You're welcome.
Well, I think you can continue, Andrea. I don't see
Okay, thank you.
so far.
We're almost to the end. Okay, so I was saying that, okay, the non-locality here has also a transverse component. This is very important for what I'm going to tell you on Wednesday. The quark fragmentation correlator is defined similarly. I mean, it's instead of having a hadron in the initial state and a quark in the final one, that's the opposite situation. You start with a quark and you have a hadron that goes in the final state crossing the cut. And this is actually well represented by the brackets here in the formula. You have a quark acting on the vacuum, and you generate a hadron in the final state with a specific momentum pH and spin sh. Then what enters in the hadronic tensor or the cross-section for DIS with sensitivity to transverse momentum is the integral of this guy here over the minus and plus components. And the important thing is that you fix the relation between K minus and pH minus in this way, so that the variable ZH that you measure actually corresponds to a quantity with a partonic interpretation, namely the fraction of light cone momentum carried by the hadron from the quark. This is the same discussion we had before involving X and X Birkin, but for the hadronization side. And again, here the non-locality has a transverse and a plus component. Okay, so in order to close this first part of the lectures, let's see what the quark transverse momentum PDFs are. Let me go back to this slide first. And again, so the phi function, the correlation function with x and pt dependency is non-perturbative. So as any other non-perturbative object, let's parameterize it in terms of what we know, namely the vector, the momenta, the spins in the game, momenta for quarks, momenta for hadrons, everything that you can think about. If you apply the symmetries of QCD and you shake everything very well, what you get is at the composition of the phi correlation matrix, it's a function of x and pt, in terms of 8 functions at leading twist, which are the TMD particle distribution function for a spin 1/2 hadron. I know that some of you might not be fully satisfied by these statements, but I'm gonna leave it to the recitation sessions to show how these things actually work. I mean, it's an interesting calculation, but I didn't think it could fit well in these lectures, also because of this remote setting. So if you are curious about how this shaking with the symmetries of QCD work, you should patiently wait until the recitation sessions or maybe the next lectures. Let's see. But anyway, so you have 8 of these functions. The black one also show up at the collinear level. You remember that for a spin 1/2 hadron, we had 3 collinear quantum distribution functions, namely F1, G1, and H1. The other ones are only transverse momentum dependent, so they don't survive at the collinear level. So the red ones are time reversal odd, namely are process dependent. The Sievers function F1T perp, and the Bohr-Mulder's function H1 perp. So this table here with ULT means that you're considering, for example, for the Bohr-Mulder's function, a quark with a transverse polarization inside a nucleon with an unpolarized nucleon. Vice versa for the Sievers function, you have an unpolarized quark in a transversely polarized hadron. So this is the way you should read this table. Same thing for spin 1. But as happens for the structure function, if it includes spin 1, you have many more distribution functions, TMD distribution functions. So you have 3 more rows which are related to the tensor polarization of your spin 1 hadron, and you have other 10 TMDs at leading twist. So I don't think, so already the spin 1/2 TMDs are not well known, both from the theory and the phenomenology point of view. The tensor polarized ones are completely unknown. I mean, we know that we can define them, but no one has ever studied them in great details. There are people who work on these topics, a few of them, but I don't think we are at the same level of accuracy for the knowledge of these functions with respect to the other 8 for the spin 1/2 case. For the delta correlation function for the hadronization part, instead, we have 8 fragmentation functions dependent on transverse momentum. There is the same classification as I explained for the parton distribution functions, and the color code is the same, so the red are time reversal odd. Let me tell you that, for example, this one, which is pretty famous, is the so-called Collins functions, the Collins TMD fragmentation function. It tells you, describes you the, let's put it in quotes because it's not really correct to say that, but the probability to extract a transverse, to generate an unpolarized hadron from the fragmentation of a transversely polarized quark. Okay, let's now show how to connect the structure functions with the TMDs. For example, the unpolarized structure function is a convolution of the unpolarized TMD PDF with the unpolarized TMD fragmentation function. And Luca, you see that here, if you apply the definition of the convolution here, the omega factor is 1, if you compare these two formulas here. If you take another unpolarized structure function, but with the cos2 phi as mutual dependence, that's a convolution of the Bohr-Mulder's TMD PDF and the Collins function, but the omega factor is this complicated form here, which is purely kinematical. Nothing that you have to fit or model, is just something that comes out of the calculation. It's purely kinematical. For the Sievers structure function instead, which is a structure function for the scattering of an unpolarized lepton beam over a transversely polarized target exchanging a transversely polarized photon and using this specific azimuthal modulation, then what you obtain is the convolution of the Sieverts TMD PDF with the unpolarized TMD fragmentation function. And the kinematical factor is simpler, the dot product between the quark transverse momentum and the direction of the fragmenting hadron. And so on and so forth. You can have this kind of expression for all the 18 structure functions for polarized semi-inclusive deep-elastic scattering. And if you're interested, I can give you the link again, but it's on the previous slides if you want to check out the expressions for all of them. Okay, so the take-home message here is the following. The left-hand side of these equations, the structure functions, can be measured experimentally, whereas the right-hand side is expressed in terms of partonic quantities, namely transverse momentum distribution and fragmentation functions. So you can interpret in terms of hadron structure and hadron formation, something that you really measure. And so this is the core, this is the meaning of transverse momentum imaging, measuring something that you can interpret in terms of distributions related to quarks and gluons. And eventually, this is what you're gonna do when you apply TMD factorization to the cross-section of a process like semi-inclusive deep-elastic scattering. You get data that you measure here, the sigma. You get a convolution of a TMD PDF and TMD fragmentation function, your partonic maps that can be extracted from data. You remove whatever you can calculate in perturbation theory, like the hard functions or other components of the TMD PDFs that I didn't discuss today. And eventually you're left with your information about hadron structure and hadron formation. So I think that's all for today.
Thank you very much, Andrea. Well, we have several raised hands. Let me start by...
I don't know what's your cutoff time, by the way. Sorry if I want to...
12:30, we can go a bit more, I mean, because then it's coming the lunch break.
Okay.
Not much longer, but...
Yeah. No, that's just to know.
Well, first raised hand is by Andrew Dodson. Go ahead, Andrew.
I have a question. So on in DIS, it looked like the hadronic tensor is symmetric. Is that correct?
For the unpolarized part, yes.
Right. So what I don't understand.
No, sorry, go ahead.
What I don't understand is how it can then be expressed in terms of a commutator of currents that is antisymmetric, or is it just like time ordering fixes that or something?
You definitely have a time ordering there. I didn't write it down. That's a good point. Yeah. Yeah. There is a yeah. This is something that you can check also in Muta's book, for example.
Okay.
Can you hear me?
Yeah, I can hear you. I'm just
thinking. Okay, sorry. Yeah.
Sorry.
No.
Because the commutator would be antisymmetric, right? So I imagine there needs to be something else to fix that.
Well, anyway, so if you include polarization terms, you'd also have an antisymmetric part of the hadronic tensor. Both the leptonic tensor and the hadronic tensor have an antisymmetric part as well, which is related to the polarization. So if you do the fully polarized case, it might not be that strange to have also, to have a commutator. I mean, this is a good point. I didn't think about it. There is definitely, so the time ordering is needed for the OPE to work.
If you allow that,
yeah, go ahead, please. Who's talking?
In the commutator, I mean, if you work it out a little bit, the mathematics, you will realize that one of the two terms in the commutator gives you a delta of conservation of momentum that never gets zero. So the term per se is a zero.
So the commutator is a difference, and one of the two terms actually is zero. So is relevant. Yeah. That's a good point. But the OPE itself is applied to the commutator.
Yeah, I mean, that's the point. You just introduce the commutator to be able to apply OPE.
Yeah.
I see. Okay. Thank you.
That's a good question. Thank you. Thank you, Victor, for contributing.
You're welcome.
Now we have a question by Daniel Adamiak. Go ahead, Daniel.
Yes, thank you. So when you write down the cross-section for DIS in terms of the structure functions and your projectile and target are unpolarized, then you have the two structure functions that depend on the polarization of the photon. But when you polarize projectile and target, you no longer have the structure functions dependent on the polarization of the photon. Could you comment on this a bit? Like, does polarizing the projectile and target fix the polarization of the photon, or what happens to that?
Yeah, I believe so. Since you're scattering a lepton, a polarized lepton, I mean, yeah, you have to have the right contribution from the polarization of the photon in order for the partonic subprocess to work. So that selects only one of the two polarization states for the photon, I believe. Yeah.
Okay, cool. Thank you.
Thank you, Daniel. Now we have a question or a comment by Victor. Go ahead, Victor.
Yes, I have a question on this difference on the hadron tensor for spin 1 and spin 1/2. I don't see why there is a difference between these two things, because when you write the expression of the hadronic tensor and you use things that I think they are not related to spin, right? I mean, you use this parity conservation, electric charge conservation.
Yes.
Why there is a difference?
Yeah. So okay, maybe so this is a good point to repeat. Let's go. Sorry, let me go back to DIS.
Sure.
So the reason is written here. So okay, so it's true that the symmetries are exactly the same, but this is what happens if you don't consider at all the polarization. You have 4 contributions. If you include the spin vector, you can have, I don't remember how many more terms, like with E, D, and F coefficients, for example, how many other Lorentz structures you can have. But you can build structure with the spin vector. If you include the tensor polarization, so if you include another object in the game, another Lorentz structure, then you can have even more structures related to the spin 1. And those structures are only there for deuteron. They are not there for a nucleon. So that's why you have more structure functions and more parton distribution functions for a deuteron.
Okay. In one of these bibliography, it will be this a little bit more developed, right?
Oh yeah. So let me point out the paper. I point out to you the paper here, this one.
Perfect. Yeah, because I
this
think
is slide 36.
Yeah, I think that there is something on this rank that in these tensorial things that I'm not getting exactly. So, thank you.
You're welcome.
Thank you, Victor. Now we have a question from Patricia. Please go ahead, Patricia.
Okay, well, thank you so much for this lecture. It made me connect a lot of dots that I had missing during this year of my PhD. So thank you so much.
I'm glad to hear that.
So like my first question is maybe something that you already have answered, because it's connected to the parametrization of the hadronic tensor. So like I wonder if it's explaining this reference that you cited, because I would like to see whether it can be connected or not to the cordon decomposition thingy that I mentioned. Maybe in this paper of slide 36, they explain in detail the parametrization of the hadronic tensor. Is that correct?
You can check definitely in one of the references, yeah. And I mean, drop me a message in Slack, please, so that I'll remember to do it as well.
Okay, thank you. And then my second question is about the diagrammatic approach, I think it was called. I would like to know if you have an answer to why you say that it only works at lowest order compared to the TMD factorization of the cross section.
I mean, because, okay, yeah. The focus of that approach is to organize the non-perturbative information. So it's not really to resolve the structure in perturbation theory of the cross section. So the people who worked with it were really interested in understanding, for example, what is it? Sorry. Yeah. So the people who worked with it and developed this approach were interested in understanding how to organize the non-perturbative information. Those were like the early days of semi-inclusive DIS. Not many measurements were active at that point. But I mean, today now we have many more. We have a lot of not a lot, but we have plenty of experimental information to quantitatively extract maps from data. But in order to do that precisely, we need also to correctly calculate and remove from what we are considering as non-perturbative information, everything that can be calculated. So this is something that I will explain later on, but the concept is already pretty clear and simple, I would say. I mean, if you want to fit a non-perturbative quantity, and what you measure is a combination of perturbative and non-perturbative, then you have to remove like the perturbative information. And the right tool to do that is TMD factorization, because it allows you to separate, to factorize what you can calculate from what you cannot, because it's non-perturbative. So the diagram, to respond to your question, the diagrammatic approach was a way to basically study the twist expansion of these observables of this of the hadronic tensor, whereas TMD factorization is more quantitative because it tells you also how to fixing the twist, like consider, for example, only this diagram. It tells you properly how to extract your non-perturbative information from the data.
So you say that the diagrammatic approach is like an old-fashioned way of doing things compared to TMD factorization?
It started before that, so maybe you could say that it's a bit more old-fashioned. In a sense, it's true. But for example, it's not useless, because it allows you to categorize and to make sense of the higher twist contributions that we don't know how to treat in TMD factorization yet.
Okay.
So there are actually some research directions in which people try to they already know higher twist contributions from the diagrammatic approach, and they try to make sense of these contributions using the factorization approach.
Okay, thank you so much.
You're welcome.
Thank you very much, Patricia. Do we have any more questions? I don't see any raised hands. Then maybe it's a good moment to call it off the morning session. I would like to thank you, Andrea, for these two lectures. They were very nice, very instructive, very well organized. And I guess I'll see you tomorrow.
Sure. On Wednesday, right? Don't make me lecture tomorrow again.
Sorry.
I'm joking. Okay. I'll see you. Maybe I'll see you later in the Gather Town configuration. But I don't promise anything. But we'll see.
Very good.
Okay. Goodbye to everyone.
Thank you.
Thank you. Goodbye, Andrea.
Bye.
Bye.
Hi, Scott. Good afternoon. How are you?
Hello, I'm well.
Hi, Elena. Is Elena or?
Yes, Selena.
Oh, hi. How are you?
Good.
Good. Nice, nice. I'm your chair. There should be also Arun with me. Just wait. He's coming. And if you want, we can try. You can try to share the screen. So just
Sure.
grab a. Hi, Scott.
Good afternoon. How are you?
I'm good. How are you?
Good.
Okay. It looks nice.
The slides look, yes, they look awesome.
Yeah.
I've only got 3, so I'm only going to do them. But
okay. Okay, just wait. We try to start really on time, but usually students arrive really like on the edge of it. So just wait another 5 minutes.
Great.
Hi, Ellie.
Hello, good morning. Afternoon now. Good afternoon.
How are you? It's been a while.
It's been a while. It's good to see you.
Good to see you too. As you know, I was just going to say, I still have the Einstein that you gifted us.
I was just thinking about that the other day. We've improved a lot since then, so we can give higher resolution ones now.
Okay, very good.
Hi, Arun. I'm your co-chair today.
Hi,
I will monitor the chat for you today.
Oh, thank you very much. So,
Quick question.
yeah.
I have a small fan running in the background because it is almost 100 degrees in New Hampshire today, and our building hasn't turned on our air conditioning yet. Is it an annoying sound in the background? I can turn it off if it is.
No, we don't hear anything.
Okay, perfect.
Yeah. I was going to say, Alberto, remember the Frontiers and Careers that was organized 5 years ago? We went to New Hampshire, and that's when she gave a tour of our polarized target lab.
Oh.
It's a small world, right? Okay, so what time is it? It's let's see.
We got 127 on my end.
We got some time. We have 34 participants. We'll wait for 45 or so. That's the threshold. Okay, so perhaps in the meantime, I describe some of the things that that some of the way people have been asking questions, and we could talk about what you're comfortable with.
Sure.
People have been posting questions on the chat, and we've been pointing them to the speaker as they happen. They've also been raising hands and waiting for the chair to discover that, give those questions to you. Or would you just prefer just unmuting microphone and just asking you on the spot? Whatever.
Yeah, so I've got the chat open. I've also got Slack open. And then I'm running out of computer real estate, so I won't see hands up. But if somebody else is keeping a track of that, that could be helpful. And so people can submit questions that way, or if you want to submit something, have a question verbally, particularly if I keep going on and miss that there's a question, please feel free to interrupt verbally, and we can take a minute and review any topic.
Okay, sure. We'd notice any other questions that are put on the chat and follow them up with you as we go along.
Actually, we have a question from the chat. Elena, if you can post like your slides before the lecture on the Slack channel. I think that was the question. So if you can.
Yes, give me just a moment.
Yes, thank you very much.
Although I will give everyone a heads up, as I mentioned earlier, I've only got, I don't know, very few slides for today, but I will post what I have.
Let's say today are your first 2 lectures, and then you're coming back on Friday for 3 more, right?
Yes.
Okay.
No, sorry. Thursday is 1, and then 2 on Friday. Or did the schedule change?
Yes. Yes. Right.
It is not allowing me to upload them, the slides. I do not know why. I apologize.
Well, Ellie, if you send us by mail, then while you talk, we post them.
Given that we're about to start, is it okay if I post them afterwards?
It's probably okay. But if you can just drop them in the email, I will take care of everything else.
I will. It just takes a couple minutes for my email to open up and everything. And
okay.
I know that we're just about at starting time, so I don't want to.
Okay, then we can do that later.
Apologies. I will upload them afterwards. Just most of the slides for today are just kind of helpful things and not so much on the topic itself. So they're more resources that you won't necessarily need for what I'll be talking about today.
Oops, we can't hear you, Alberto. You may be muted.
Are these slides what you sent me like 10 days ago? Because then I posted those under her name in the main page. There are 2 links on the main page of HUG with the resources that she was showing before, just 2 seconds ago.
Yeah, that's the vast majority of what I have on the slides.
Okay, so I guess we can go ahead and start the lecture. I think we have close to 52 participants. Okay, so it gives me great pleasure to introduce Ellie, or Professor Elena Long. I remember from 5 years ago when we first visited your polarized target lab, you gave us similar lectures on peanuts and donuts. And you talked about polarization of the neutron and how it's easy to remember that in terms of that. And we welcome you back after 5 years. Okay, welcome you back to give us a lecture about a lecture series about physics with light polarized ions. So welcome to Hugs, Ellie, and the floor is yours.
All right, thank you very much. I'm excited to be here. Happy Pride Month, everyone. I'm coming to you from my teaching void. That'll make more sense in a little bit. Some of the peanuts and donuts we won't get talking about probably today, maybe a little bit, but we'll save some of that for one of the later lectures. What I want to get started with today is, even before diving into the physics of dealing with polarized light ions, is just to provide some resources to all of you that when I was in your position and I was a graduate student, these are a number of resources that I found extremely helpful. So I want to make sure that you have them available as well. There are 3 books in particular that I found extremely useful. Particles and Nuclei by Pove. And right now, for the topic that I'll be talking about, the most recent 7th edition actually has a number of new JLab results that have come out over the last 10 years or so. So I would recommend that one over the 6th edition, although the 6th edition is also fantastic. There's also these 2 what are called brief books, the Data Analysis Brief Book and the Particle Detector Brief Book. These used to be online. I posted 2 links here to the Internet Archive's older version of them. What's really nice about those is that it's a great, super short reference. It's like an index for a lot of the different types of equations and topics and terms that you're likely to come across in your career as a graduate student in nuclear physics. So it's really helpful to have that as just kind of a quick thing to flip through if you're double checking how equations should be put together. You can kind of flip to one page, go there, and just double check it. Super useful. For handling papers, finding papers, looking for them, the two links that are probably the most useful immediately are Inspire and the archive. Hopefully you know both about those already. You'll likely be doing work with Root if you haven't done a little bit of that already. So the Root website is posted here as well. And lastly, another book that could be helpful, this yellow one in the background, is Technique for Nuclear and Particle Physics Experiments. If you're ever curious about why we use some of the detectors that we do or how they work, and a lot of the details on that, this book is really good for giving you a nice overview of how the detectors that we use to do experiments work on kind of a big part by part basis, and you can use that for debugging equipment and things of that nature. So just kind of a heads up, those resources that were really helpful to me, they may be helpful to you as well, and those will be posted on Slack afterwards once I figure out why the upload didn't work, and should be posted somewhere on the website under my name. The next thing, actually, before I get into the next thing, I forgot to say a little bit about my own background. So my research history, my graduate work was at Jefferson Lab, where I did research on experiments using polarized helium-3 to better understand the neutron. I've most recently been working on building a tensor polarized target here at the University of New Hampshire for a couple of experiments coming up in Hall C. That uses a very different polarization technique, but still doing polarization. We'll talk more about details of both of those, what those look like. I've been involved with experiments to look at asymmetries to understand how the neutron exists inside of helium-3 and those complications for measuring the internal electromagnetic structure of the neutron. And then for the tensor experiment we have coming up are a deep and elastic structure function and a quasi-elastic short-range correlation region experiment. If those words don't make a lot of sense to you now, if you're unfamiliar with them, don't worry, we will come back to them. What I am curious though, before I go any further from all of you, either in the chat or on Slack, I would like to know what experiments you think that you will be working on for your grad programs. And particularly, what would be helpful as I prepare the last day of talks, I want to try and help you all as much as you can. So if you're doing anything in particular with spin polarized experiments, or you're planning on doing them, if you know what those experiments are, please go ahead and share them with me now, either in the chat or in Slack. That's some from GlueX, EIC phenomenology, EMC effects, SpinQuest. I'm very familiar with SpinQuest. Excellent, excellent. Keep them all coming. What I will do is I'll save the chat afterwards, go through the list of all of them. And my hope is to take the experiments you're working on and tie them in more closely to the last two talks to make sure that the presentations I'm doing is really helpful to all of you. So thank you very much for sharing. I appreciate that. Now, just some more helpful, just kind of tips and tricks of nuclear physics generally, that also are things that are not always immediately obvious. This might seem very basic for all of you, but just in case, if you're not already doing this, some recommendations on just how to do things in nuclear physics. Just useful tips and tricks. One, always make sure that you're checking units. I mean, we learned this from intro physics. Your units will help you anytime where you need to go through a paper and understand what it is you're coming out with. If you really want to understand what it is involved with, work through the units backwards to make sure that they are tied into things correctly. And if you're trying to build a simulation, let's say, and trying to export a cross-section, there are multiple types of cross-sections. So by double checking how your units come into play and different theory models that you'll put into your cross-section use different units as well, going through doing unit analysis seems like a simple trick, but it's one that I find even to this day using over and over and over again to be helpful to do. I'm sure most of you know that the radius of the proton is about 10 to the minus 15 meters, which corresponds to about a femtometer, which is a unit of length that you'll tend to see for our field. Whenever we are talking about energy or mass or momentum, we always want to use either MeV or GeV. And anytime you're doing math out, wherever there's a speed of light, c, it's helpful to always just leave that as c and never plug in, 3 times 10 to the 8 meters per second. The reason for that is c's often will cancel out or be able to be transformed into easier units when you're trying to understand different components. So 2 kind of quick masses on here, worthwhile keeping in the back of your head. The mass of an electron is about half an MeV, and the mass of a proton is on the order of about 1 GeV. If you're doing anything with York and X with scaling variables, with fixed target experiments, that mass of the proton one, you will see that one over and over and over again. So that's a good one to get into your head. Related to that factor of C I mentioned, it's always useful to group H bars and C's together. And the reason for that is that if you multiply H bar times C, it comes out to an almost nice round number to within a couple percent of about 200 MeV times femtometers, which means that all of your H bars, all of your C's, you can turn into energy and length. And energy and length are much easier to deal with than H bars and C's. Related, if you have other units, particularly related to charge, a good trick that will usually work for getting rid of units of charge and turning into something unitless is to use the fine structure constant alpha, which is 1 over 137, very, very closely to just this unitless number. So if you're doing out, different cross sections, whatever you're working on, you find that you have charge you're keeping track of, and you don't want to keep track of, coulombs or whatever. If you convert it into units of alpha, you can just use the unitless 1 over 137. So that's a helpful tip and trick to use. For cross sections, cross sections have units of area. The unit for that you'll most often see are millibarns, which are 10 to the minus 27 centimeters squared. Steradians, if you're not familiar with them yet, define a solid angle. You can think of that as kind of like an angular area. So the capital omega is equal to the geometrical area that it would be sweeping out versus r squared in steradians. You can also think about it as how wide are you looking in theta, how wide are you looking at in phi, the in-plane and out-of-plane angle for any given experiment. We'll mention a little bit more about that as we go forward as well, but if you're not familiar with steradians yet, this is what steradians are. For polarized targets specifically, that's where this next unit comes in. Planck's constant, not h bar, but just normal Planck's constant, divided by Boltzmann's constant, is equal to very close to 5 times 10 to the minus 5 Kelvin per megahertz. It is also equal to 1 atomic specific heat constant, but having a number of 5, 10 to the minus 5, I find that a very easy number to remember, and especially when doing anything with polarized targets, this particular unit will come up over and over and over again. Anytime you're dealing with units, I mentioned this earlier, if they don't seem like they're working out in a paper, oftentimes we will put our units into natural units where h bar is equal to c equal to 1. If you know what the units are supposed to be, and the paper is in natural units, you can often work backwards to figure out where the units need to go into play. It's usually missing H bars and Cs, which are 200 MeV times femtometer. So if you know that factor, you can usually work backwards to plug in those units and come figure out what's missing in an equation if you need to put numbers into it. And then the last kind of just general nuclear physics trick, a lot of what we do is going to be highly relativistic. And what that means is greater than about 10 MeV for electrons or about 20 GeV for nucleons, for protons and neutrons. And in that case, your momentum times C is about equal to E. We can usually ignore the rest mass if we were in a highly relativistic case, which makes doing simple calculations, back of the envelope calculations, a lot easier. So those are just some simple tips and tricks that I found over the years. And I'm going to turn that off for now. And for most of the rest of this, hopefully you can all see my screen clearly. If not, please try to make it as big as possible, because the next thing I want to talk about in regards to things that can be helpful are useful equations. So the first one of these, and again, some of this might be review to what you've seen already, but I just want to make sure that we're all starting from the same starting point. First one of these is our form momentum transfer Q squared. So this is approximately defined as 4 times the incoming energy of your beam. If you're at JLab, it'll be your electron beam, times the energy of the scattered beam, times sine squared of the scattering angle of your electron divided by 2. And this is our form momentum transfer. The reason why this is particularly useful is that this is closely related to the resolution, or how big is the thing that you're looking at different Q squared. As your Q squared increases or decreases, that changes the resolution of what it is you're able to look at. So proportionally, your resolution, the wavelength of your probe, of your electron probe, is proportional to 1 over the square root of Q squared. So if Q squared gets bigger, that's going to mean that your resolution gets smaller, or vice versa. So this is why Q squared is such a useful unit that you'll see over and over and over again, many different aspects of what we do in JLab physics. Related to that is not the form momentum transfer, but the energy transfer nu. Sometimes you'll also see this written as omega, just 2 different Greek letters used for the same thing. And this is your incoming electron beam energy minus your outgoing beam energy. And this is our energy transfer. So energy transfer, why that's useful, you can kind of think of that as how hard did we hit the thing that we're probing with our electron probe. And the last one that I'll mention is Bjorken X variable, which is equal to Q squared over 2 times the mass of a nucleon, which we usually use the mass of a proton for that. That's why I said that mass of the proton, that 938.272 number, is useful to keep in your head. Anytime you use X, that's where that'll go. And we have our energy transfer nu in here as well. So this is our Bjorken X scaling factor. And it's more accurately to say that Bjorken X is a measure of how much momentum did the thing we hit carry related to the momentum of a proton or neutron. A little bit of a hand-wavy way of thinking about it is you can roughly think of it in terms of how big was the thing we hit with our electron probe. And I will note too that each of these are assuming, especially with X here, is assuming that we're looking at a fixed target experiment like Jefferson Lab. There are modifications to these that will occur if you're using a collider versus a fixed target. I didn't prepare this as part of my things to upload, but I'll upload for anybody interested a conversion of these variables between fixed target variables to collider, depending on which world you're going to find yourself working in. When we're looking at these variables, we're using it to describe processes that we often will look at in terms of a Feynman diagram. So in our case, we have electrons that are interacting usually with either a nucleon or nucleus or maybe something smaller inside of it. So if this is, say, a proton that we're looking at hitting, and whatever kind of comes out the other side. When our electron interacts with it, it's going to exchange a virtual photon with it. The electron itself will have different momentum afterwards than what it came in with. So the incoming beam momentum we could write as K equal to, so this is a 4-vector momentum K, where the first term is the total energy that the electron has, and then the next 3 terms are the 3 momentum of it. Similarly, for the scattered electron, we can do something very similar, but instead of K, we can write it as K prime, where we would have our E prime and a 3-vector K prime. When the interaction occurs through our virtual photon, we can describe that through a 4-vector little q. And the 4-vector for little q is equal to our energy transfer nu for the first term, and then a 3-vector q for the remaining 3 terms. This 4-vector q is related to this 4 momentum transfer q squared by a negative sign. So our big Q squared is equal to negative little q, this 4-vector here squared. And the reason we do that is because we don't like dealing with negative numbers because it makes plotting things a pain. So by getting rid of this minus sign through this definition of variable, it helps us to avoid negative signs in a lot of plots. This is the major reason for it. For our let's say our proton that we're hitting here, this would have momentum P, which would be the energy of our proton and our 3-vector momentum of that proton. And if we're doing a fixed target experiment, then this momentum, the energy of it in the beginning, for a fixed target, if it's not moving, if the proton is stationary and in place, that means that its 3-vector momentum would be 0 for all 3 directions, and that its energy would be just the rest mass energy of it. It wouldn't also carry the energy associated with the momentum as well. So it would just be the rest mass of that proton. And this would be true for fixed target. Sorry, I'm just rearranging my screen briefly, see if there's any questions, and I don't see any yet. Perfect. One last variable to define is the invariant mass W. And usually this is written as the square of the invariant mass. This is equal to mass squared plus 2 times the target mass squared, mass of the target, times nu minus q squared. And this is the invariant mass of our hadronic system. Hadronic means, being made up of hadrons, meaning made up of quarks and gluons. So for the proton, for the neutron, for those sorts of particles. Any questions on the kind of basic equations? Shouldn't it be written as MP? It could be written as MP. I wrote it just kind of shorthand here without, but if our target is a proton, then we can do it as MP. If we're looking at invariant mass of something heavier, we could use the mass of the target. It depends on whether you want your invariant mass to be related to the mass of the total target or the mass of the individual nucleons in it. Would depend on whether you want to put MP here or the mass of your target. There are reasons for using one way versus another, depending on your nomenclature and what's most helpful for the application that you're using. Typically, if you're doing anything on the proton directly and not using heavier nuclei, you would use MP though, that's correct.
So Ellie, maybe I can ask a question in the meantime.
Yeah, of course.
How are you doing this? There's a plastic board and you have the camera behind the plastic board and you're getting a mirror image of that onto the screen, or?
Yeah, I actually have a physical mirror that the camera is aimed towards. That is on the other side of just a sheet of plexiglass that has an LED strip just around the outside of it. This was my attempt to get as close to eye contact as possible in the virtual world we've been living in this past year and a half.
This is fantastic. We appreciate the patented technology.
So Elena, if you can send a picture of the making of, just to see how the setup works, it would be great. I'm Astrid, by the way.
Yeah, I'll take a picture of the setup afterwards.
Okay.
And you also see that when you're talking, I'm kind of looking off to the side because my monitor is over here and not directly in front of the camera. So apologize for that part of it.
The school managers were having bets running in the background to see who can guess the setup best.
All right. Let's see. Another thing, probably review, but I want to make sure that we go over it anyway, is if we look at what a cross-section looks like versus different Bjorken X. So if we go versus Bjorken X and look at how the cross-section changes, as I mentioned before, Bjorken X, you can kind of hand-wavy think of how big was the thing that we hit. On the larger end of Bjorken X, we will have there will be nothing for a cross-section until a certain point where you'll tend to get a large spike. And that happens at X of about A, where A is equal to your number of nucleons, your number of protons plus your number of neutrons. This is our elastic peak. Is what this term here is. A little bit lower in X beyond that, we'll have a series, depending on your nucleus, of smaller peaks, which are where the nucleus itself, you're looking at different resonances, different excited states of the entire nucleus of what you're hitting. So these are the nuclear resonances. And one of my lights just died. Apologies for that. Hope we're okay, even though I'm a little bit more in the dark. There we go. Get that back. Nope, doesn't want to be. We'll figure that out later. I think that's probably heat related because it is warm in here. Anyway, a little bit lower in X are these nuclear resonances, which are where we can probe the excited states of the nucleon. So kind of within this whole region, basically what we are probing is the resonances of nuclei as a whole, of groups of nucleons. So in this high X region, we are probing whole nuclei, whole nucleus inside of something. As we go down in X a little bit more, there tends to be a flat region that is very similar for all nuclei that go past X of 1 before it starts coming up again and has a much broader peak right around X of 1. This broad peak is the quasi-elastic peak. And it's typically brought in for anything heavier than hydrogen, which is 1 proton, because your X of 1, if we kind of think about that as, how big was the thing we hit, when we're at X of 1, what we're doing is, in this quasi-elastic region, we are probing individual nucleons, individual protons or neutrons. This in-between flat region, some of you might be working on that. This is also known as the short-range correlation, or SRC region in here, which probes structures that are greater than a single nucleon, but less than a whole nucleus. So it's usually looking at structures that are high momentum pairs of nucleons in a unique state called the short-range correlation. We'll probably talk more about that later on. So our quasi-elastic then is hitting individual protons or neutrons, going down a little bit lower than X, just like we had the nuclear resonances. We get nucleon resonances in this region. The one that's usually the biggest that you'll see most often is called the delta resonance. And you can think of the delta as, roughly an excited proton or an excited neutron. Question came up, I thought X between 0 and 1 is just for scattering off of a proton. You can also do it off of a neutron as well. So 1 is defining, we wrote our X, you'll recall, as q squared over 2 the mass of the proton times nu. So when the momentum of the thing we're hitting, roughly how big is the thing that we're hitting, is it's directly divided by the mass of a proton here. So when X is 1, that would be as if you're hitting an entire whole proton. As we go smaller in X, the first thing we're going to get are these excited states of our proton or neutron. And then smaller than that, we get into the region where we start hitting individual quarks and gluons on the inside as we get to very low X. And this is what's called the deep inelastic scattering, or DIS region. And that starts turning on below X of about 0.7. There's not quite as a sharp transition into it, but about 0.7 is a good ballpark for getting into the DIS region. As I mentioned, this DIS region in particular, what this probes are the quarks and gluons inside of the proton or inside of the neutron. So for the different kinematic regions, if you're going through a number of different physics talks, you're most likely going to be hearing about probably deep inelastic scattering, quasi-elastic scattering, short-range correlation, maybe elastic. Some folks are still doing work in there. I'm still doing some work there, although it's not as much is happening on the pure elastic front as much these days as has been done historically. But occasionally there's still work to be done on some of those projects as well. Question, can we get the boards in the shape of the slides? So related to the notes that I've got a series of notes that I will upload and scan and post in the Slack as well, assuming I can get that working. So that way you have the notes of the presentation as well for where all these are coming from. So these are kind of the major kinematic regions that when we're doing JLab type experiments or different kinds of popular nuclear physics experiments that are happening now, these are the regions you'll most likely hear them talking about: DIS, quasi-elastic, short-range correlation. And now you can use this Bjork and X term that when you see these terms, you can say, oh, if we're in the SRC region, it's X greater than 1. We're probing something bigger than a single proton or neutron, but smaller than an entire nucleus. Or if we're in deep inelastic scattering, that means that we're probing the structure of what individual quarks and gluons are doing inside of things. Or if it's quasi-elastic, it's looking at what the nucleon, the proton or the neutron as a whole is doing. And as I'm erasing this, this is another good time for questions if there are any more. Previous lecture, we had that for sufficiently large q squared, x is a momentum fraction that thus can't be bigger than 1. So this gets back to what I had mentioned earlier, that my caveat, all of my background so far has been in fixed target experiments, not collider experiments. And for JLab physics, which is just my background of it, the way that we write Bjork and X is how I define that as being related to the mass of the proton. So if we have, say, a deuteron, which is a one proton, one neutron pair as the nucleus that we're hitting, then its total momentum could at most be 2 times that of a single proton, because mass of a proton, mass of a neutron would be double that. So that's why with the definition of X that I've been using, which is directly scaled by the mass of a proton here, which is typically what we use for JLab for fixed target experiments. This definition is what allows for X to be greater than 1. You could also, depending on what you want to do, not have this be the nucleon or proton mass, but be the mass of your target as a whole. In this case, where it's the mass of your target as a whole, then what you're saying is exactly true, that this could not go greater than 1. And in fact, there's a slightly modified version of this for colliders that I'm not remembering off the top of my head, so I apologize, I won't write that, but I will include it in the Slack later today. That is more useful for colliders than for fixed target. Just in the nomenclature that I'm using, just because my background is mostly fixed target, that's why I'm using it the way I am. And also why this description of the cross-section that I just drew is dependent on this being related to the momentum fraction of 1 proton or neutron. In the case where it's your total target and your target is not a proton, it's something heavier, then those exact numbers will change. But that was a great question. Thank you.
Ali, there's another question right before the one that you just answered, which is which of these regions are better understood?
Oh, that's a good question. Probably the best understood for the most part is probably the elastic region, since that's tended to require less energy and was what a lot of the earlier colliders were, or a lot of earlier nuclear physics had been focused on. There is a lot of excitement these days in the short range correlation area to explain really what's happening with these pairs of nuclei that seem like they enter into this state where their wave functions are overlapping and they're extremely close together at very small distances and moving extremely relativistically. There's a lot of kind of ongoing mystery there that we're still trying to work on understanding. For quasi-elastic, actually, for the quasi-elastic, deep inelastic, I'm going to put that question on hold for now because we're going to get into that. I don't know if we'll get into it today, but we will definitely get into it on Thursday if we don't get to it today. And we'll go into kind of where those different aspects are, looking at it from a spin perspective of kind of where we understand spin structure in these different kinematic regions up to kind of where we are today and where we still have ongoing questions where we don't understand it. So we will get there. All right. The next topic, since this is all about polarized light ions, is going to be an introduction to spin. So again, this might be a little basic for some of you. I apologize if that's the case, but I want to make sure that we're all on the same page so we can get into the more advanced topics and make sure that we're bringing everyone along. So the first thing to note with spin is that spin is intimately connected with the magnetic moments of particles. So whenever we're talking about spin, there is a direct connection to the magnetic moments of what we're talking about. And we can think of why this is, we're looking in quantum spin for what we're going to be doing, but if we just kind of take a step back and think about spin classically, of how that relates to a magnetic moment. So if we look at this classically, then a magnetic dipole moment is a vector that relates a torque felt by a magnet inside of an external magnetic field to that external field. So if you put a magnet inside of an external field, so if we have some big external field and we put some magnet that has a north pole or a south pole, because that would be a dipole magnet, it will want to orient itself along the magnetic field. So it will feel a torque until it gets aligned. So that torque vector is related to the magnetic moment mu crossed with the external field B. And that's just saying that when we put a small magnet inside of a bigger magnetic field, it's going to want to align so that the magnetic fields are oriented with one another. If we look at not a bar magnet, but if we think about creating an electromagnet, so if we have a loop of wire that has some current I going through it. Remember again from intro physics, this is another way we can create a magnet. You can use the right-hand rule to determine, if this was kind of coming in and out this way, we could use right-hand rule and say that's going to create a magnetic field pointing up and down. So the magnetic moment is going to be along that same axis. So going to draw that out of the plane. Our magnetic moment mu will be pointing along that magnetic field induced by these charges going around in a circle. As they're going around, classically, they're mapping out some area A. So if we take our definition for torque on a dipole, but now instead of having it just be like a bar magnet, we have it be a loop of wire that we're looking at, we can use this to determine our magnetic moment as being equal to the area that it's mapping out times the current that's flowing through it. And this will be in the direction from the south pole to the north pole of whatever the induced field is. So this is kind of our first connection where we have charges that are moving around. It's like they're spinning around, they're in this big orbit, is creating a magnetic field. So it's kind of a classical intuition for kind of how you can get a sense of why are spin and magnetic moments connected, because anytime a charge is spinning around, it's going to induce a magnetic field, which is where the magnetic moment of that spinning charge would cause. So this gives us a kind of a classical understanding of how these things are connected. Of course, in quantum mechanics, things aren't the same as they are classically, and we have to account for the quantized or discrete structure of spin. So when we're doing this in quantum mechanics, that spin is quantized. So that means it's going to be only able to go in certain discrete steps that it's allowed in. And these are usually described solely in terms of their z component. See, there are a couple of questions still related to X. We will talk about, we'll come back to those after we do our introduction on spin. But thank you. I'll make sure to include these and write them down. So as I was saying, for quantum mechanics, we are usually defining spin by its z hat component. And in that case, the spin states are quantized into integer jumps of h bar. So what does that mean? Well, if we look at a spin half particle, and if we draw our z hat axis as coming upwards, and an xy plane drawn at the horizontal here. So if we were to kind of skew that a little bit, then our spin vector that would come out of this would be able to process about a discrete state on that xy plane. So it kind of maps out this cone structure of how this spin would be processing. And it would do similarly in a downward direction. And in fact, we could draw this as if, I'll use my markers are going. If this is drawn out onto a really bad circle or a sphere, you could think of our spin vector pointing to a particular cross section of that sphere and then going around that way. We also said that for quantum mechanics, that these jumps in quantized spin have to be jumps equal to integer multiples of h bar. So that means that going from one of these to the other has to be an entire multiple of h bar. If we define the xy plane as 0, then this upper state we could define as plus h bar over 2, and this lower state as going down to minus h bar over 2. And a lot of times for things like h bar, like I mentioned earlier, we will tend to write things, because we write h bar so often, that the shorthand for this is, you'll often see as the +1/2 state or the -1/2 spin state. So we're in spin up, that means we're in the +1/2, which is really a multiple of h bar times 1/2. And spin down would be in our -1/2 spin state. So that means in this case, our two possible spin states that we have are going to be plus or minus h bar over 2. Of course, spin half isn't the only type of spin that we can have. We can have higher spin as well. We just have to make sure that every discrete state of between two jumps of spin has to be an integer of h bar. So the next highest spin state we could look at is instead a spin 1 particle, which would again have a z hat component. It would again have our xy plane. But now, if we were to map out this up state, where that's kind of map out this region here, instead of being at +1/2, this is an entire jump of 1 h bar, which means that the next state must be the spin 0 state. And then there can be another spin state opposite down at minus h bar, or a +1 state, a 0 state, and a -1 state. So for a spin 1 particle, our possible spin states are -1, 0, and +1. And of course, we can go to higher orders as well. We kind of can keep doing this further and further to go to higher spin states. Any questions on just kind of our definition of spin up, spin down, +½, -½ 1, 0, and -1? If we want to experimentally measure spin of some particle, the way that we will determine what this spin is by measuring the magnetic moment. Since these two things are so closely tied to one another. Quantum mechanically, a little bit different from that classical magnetic moment we drew earlier, our quantum magnetic moment is equal to a gyromagnetic ratio gamma, I'll talk about that in a minute, times the spin vector s. So this term here, this gamma, is a gyromagnetic ratio. This is equal to a term called a G factor, which has the letter G, a particle's charge Q. I'm running low on magnets. Or on markers, not on magnets. The G factor, particle's charge Q, divided by 2 times the mass of the particle. So G is our G factor, Q is our charge of a particle, M is the mass of a particle. If we have a particle that is structureless, so there is structureless, meaning that it is a single point particle, and no matter how close you zoom into it, you don't see any other structure other than the point. And if that structureless particle is also a fermion, meaning it's a spin half particle, in this case, our z component of our spin would be equal to h bar over 2 times the spin vectors, which what this means in terms of what we're looking at is that its spin, if we look at the magnitude of that, would have to be, could either be plus h bar over 2 or minus h bar over 2. So if you do the absolute value, that would be h bar over 2. When the spin is equal to that for our magnetic moment, we'll find that the G factor, if we have no structure, is identically equal to 2. And what we'd have left is our Q, our mass of our particle, and if we're looking at the magnetic moment, we would have our spin from our h bar over 2 term. This is what's known as the Dirac magnetic moment, is for a structureless spin half particle. which will usually be talking about either the proton, an estimation of the proton, or the electron, or the muon. Electron and muon are much closer to a Dirac particle than the proton. But in that case, the charge of those would be the electric charge E. We would have G of 2 divided by 2 would cancel out. We would have the mass of it, and then so that would give us our gyromagnetic ratio, and our spin term would have an h bar over 2. So our magnetic moment for a structureless spin half particle is known as the Dirac magnetic moment, which is equal to E h bar over 2m. I said this is very close to being true for the electron and the muon. And if you've seen the G-2 muon results that have been blowing up in the news lately, they're looking for deviations away from this 2. And kind of a little bit beyond that, particularly for deviations away from the standard model's estimate of 2. But electron and muon are very close to having G equals 2. The proton, this was initially thought to be the case, but experiment kind of showed us that things weren't quite the same for the proton.
So Ellie, we have about 10 minutes left for the
Perfect.
lecture.
So I think that should give us just enough time to look at our magnetic moment of our proton to introduce this. So if our protons and neutrons are structureless, aka point particles, then their magnetic moment would be very similar to that Dirac magnetic moment, although we call it not the Dirac, which is usually meant for electrons and muons and such, but the nuclear magneton. And that's usually given a capital N term with its mu, but it'd be of the same general form of E h bar over 2 times the mass of our particle, but here we're looking at it being the mass of our proton or our neutron. But as I'm sure you all know, the proton and the neutron are not point structureless particles. They're made up of quarks and gluons and have internal structure to them. And that causes them to have what's called an anomalous magnetic moment. So that means that their G factor is not equal to 2. And in fact, for the proton, its magnetic moment is about 2.79 times greater than the nuclear magneton. And the neutron is going in the other direction. It's almost -2 times the nuclear magneton. So in this case, since our G factor here would come into play, this extra factor of 2.78 means that G over 2 is not equal to 1, but that's equal to 2.79, which means that the G factor for our proton, we bring the 2 over, is 5.58. And similarly, our G factor for our neutron is -3.82. Measuring the magnetic moment of the proton and finding that it was about 2.8 times bigger than it was expected. This was our first ever direct experimental proof that indicated that the proton was not a point particle, but had structure within it. And this experiment was first done in the 1930s by Otto Stern, who found this and then kicked off a century of trying to understand what is inside the proton, what are its properties, what's interacting in there. So our whole field of nuclear physics, of what you're studying throughout HUGS, a huge part of that, it comes from the fact that this magnetic moment of the proton was bigger than expected, And we're still to this day trying to entirely figure out what that means as a whole. So if we kind of take our anomalous magnetic moments and we break it up into the individual components of all the quarks and gluons that we have inside of it, then our magnetic moment, not just for proton or neutron, but for any given nucleus, if we kind of do a first order estimation of that with the shell model, it's related to the nuclear magneton, our factors of 1 over h bar, which always come into play. The sum over all of the nucleons, all the protons and neutrons inside of the nucleus, times the orbital angular momentum of those nucleons, times the orbital angular momentum g, and then the spin factor for each of them. For the orbital term, g of L is equal to 1 because protons are charged. And for neutrons, which don't have a charge, that means that you don't have charge orbiting to produce magnetic field. So g of L, the orbital term, would be 0 for a neutron. And our spin would be that plus 5.58 for protons and minus 3.82 for neutrons. So what we're going to do with later today, after we take a break for a little bit, is we'll take some of this idea with magnetic moment, which, as I said, kind of kicked off our big search for understanding what is the nature of what's inside the proton, what's inside the neutron, and look at using the concept of the magnetic moment to our concept of spin to look at what is polarization and how does that work. So that's what we'll do for the extra hour today. And then for the rest of class later this week, once we have a sense of what polarization is, how polarized targets work, we'll then look at what are the kinds of physics that we can do with these polarizations. Why is it helpful for us? And with that, with our last couple minutes, if there are any other questions before we go for break, I'd be happy to answer them.
Okay, any questions for Ali?
Andrew had a question before in the chat. I think Andrew can speak up. And
Oh, yes,
just ask
Andrew.
directly.
Yeah, feel free, Andrew.
Yeah, I just had a quick question on earlier you mentioned how X Bjorken is different for a collider experiment than it is for fixed target. And my question had to do with, well, fixed target is kind of a matter of perspective, like your frame of reference, right? You could always do a Lorentz transformation and voila, that fixed target looks like a collider experiment now. But X Bjorken is Lorentz invariant. So my question was, why would that change things for a collider experiment?
It's related to where the definition of nu comes into play. Versus if you have a fixed target, some of the terms will cancel out that don't cancel out if you're in a frame where they're kind of hitting towards each other. So I'll share a paper in Slack that actually goes through the details of how you would get X if you're doing a fixed collider, how you would go about it if you're doing fixed target versus collider. And the two big things that come out is the definition of, are we using the mass of a target or the mass of a proton? And then also the terms that would drop out in the special case where you don't have two things going towards each other, but you have one of them has its momentum being 0.
Okay, that makes sense. Thank you. I wish this talk happened first in hugs.
Andrew Dotson, and actually Luca had a question.
No, sorry, my question was wrong. Okay, I misspoken. What I want to say is that I probably figure out also. My problem was that you show this sigma plot, right? my problem is that from 0.7 to 1, we are actually looking to the excited state, not the proton. So for what I know, actually, we have extraction of PDF in this region. If we're looking to the excited state, we cannot look to PDF, but the problem I think was that this is done for proton, not nuclei. So for nuclei, we have this exciting, but for proton, no. So in case of proton, we can actually extract. So I actually figure out, sorry, I've done a dumb question, but I done by myself, sorry. That's correct, right, by the way? But,
yeah, I think you're thinking about that correctly, right? Because we're looking in
Okay.
that region where you're looking at the excited states of the nucleon when you're in that kind of X of about 0.7-ish region.
Okay.
Yeah, and 'cause
sorry.
in that region, you're kind of probing, not just the individual protons or neutrons, but the excited states of the individual protons or neutrons. And that would be the case if you have a proton target, or even if you have a larger composite nuclear target.
Okay. Yeah, the problem is that I'm encountering mostly protons. So when I see this, I was a little confused. But I solved. Thank you.
Okay. Next, Matteo.
Hi, can you hear me?
Yes.
Yeah, thank you for your nice talk, first of all. And my question is regarding the last thing you presented. Do you think that this problem, this issue about the magnetic moment of nucleons is related to subnuclear particle physics, or is more related to the nuclear potential?
Yes, to both.
Okay.
Yeah, so one of the things that we can get out with the quasi-elastic form factors is gives us information of kind of mapping out what are the electromagnetic fields inside the proton, inside the neutron. And when we do that in particular versus Q squared, if there was no structure, no electromagnetic structure, they should be entirely flat and not change with Q squared. But we do see them changing. And part of how you can interpret that changing has to do with, you could think of it of, since the quarks are charged, where are the quarks of different charges? Kind of getting a first order estimate of, where do you think the parton distribution functions might be? You don't get them exactly from that. You need to do deep inelastic scattering to get it. But you kind of get a hint of what it might be from that. But we could also build up our expectation for the electromagnetic structure, particularly at low Q squared, dependent on the nuclear potential, that we could kind of build up from there in order to figure out what it should be as our Q squared goes to 0 in particular. So it's a little bit of both.
Okay, thank you. Thank you very much.
Okay, Arjun, go ahead.
So I had a similar question. So like if we go up to low X, so we see that we have contribution from gluons also. So like on the same ground, it is the question. Like does it depend upon explicitly on X? Like the theoretical contribution that we see to the magnetic moment or this.
So if I'm recalling correctly for that, please correct me if I'm mistaken, just because it's not my main area. I think when you're looking at that, you're mostly looking in the deep inelastic region, in particular at the very, very low X region. So for the magnetic moment related to spin that I was talking about, kind of those early measurements, those are done at much lower energy. I'm kind of looking at the proton as a whole. It's just kind of indicating that because it's not, that it has this anomalous form factor, this anomalous G factor, that indicates that there has to be something that's not just the point particle there, but it doesn't tell a lot about what is that. So that's where deep inelastic scattering of understanding, where the valence quarks come from, where the C quarks and antiquark come from, and where the gluons come, especially as we probe at lower and lower X and higher energy into our really deep inelastic scattering region, that's where we can start really breaking apart where the individual quarks and gluon components are coming from, really in that region.
Okay. All right, so why don't we do this? Why don't we take a short break and we return at 2:55, and that'll be the second lecture that is going to be given by Ellie. Okay, thank you so much, Ellie. This was a beautiful demonstration, live lecture as we went up. Thank you very
And I will do my best to upload the things I promised. I'll see if I can get it working in our break.
much. Okay, thanks. Okay, welcome back to our next lecture. Perhaps Ellie can get set up in the meantime. Okay, I'm guessing you're all ready. Okay, so do you need to share any slides or check if everything is okay, or is this how you're going to start the lecture?
Oh, still
Okay.
got the screen going.
Okay, all right. So why
Will
don't
be
yeah.
just a couple more slides, but that'll even be if we get to it. I'm not sure we will.
Okay. Okay. Floor is all yours, please.
All right. So I was able to upload the couple of slides that I showed on Slack, as well as the notes that we'll be talking about today. I don't know that we'll get through quite all of them that I uploaded today. And as we do the rest of the week, I'll continue uploading more, as well as that kinematic tech note that I mentioned with the difference in X as well. So I don't really want to talk about any of those right now, but if there are questions that come up on that, please post them in Slack after our rest of our discussion today, and I'll be able to see them over the next day or two and can answer any questions on Slack there. So we've had an introduction to spin. We've looked at the connection between spin and magnetic moment, and we mentioned that in the 1930s, spin was the thing that indicated that the proton had some substructure. It wasn't a point particle, kicking off our century of understanding nuclear physics and hadronic physics and what the quarks and gluons are doing. Really started with this concept of magnetic moment and spin. So even from the very beginning of our field, doing physics with polarized light ions has been important and continues to be to today. Today, if you're doing anything in JLab especially, and you're hearing things about polarization experiments, that term polarization is what I want to talk about next. What is polarization and how do we define it? So simply, what polarization describes for us is the spin populations in a large sample of nuclei. So it gives us a sense of how many nuclei are spinning in the same direction as each other. And what is the orientation of that spin direction? So we saw for a spin half particle that could either be spin up or spin down. For a spin one particle, it could be spin up of +1, spin down of -1, or spin 0 as well. We'll talk about those. And then higher order spins happen as well, and you can kind of continue on from the tools that we'll be talking about for the rest of today. So let's start with an easy example. We'll start with proton spin. And part of why this is a little bit easier is because the proton is a fermion, meaning it's a spin half particle. So we only have to deal with 2 spin states. So let's say we've got a large sample of N protons, which are hydrogen nuclei. So we have N number of them, and they're placed in a magnetic field where some fraction of them are going to be aligned with the magnetic field and some fraction will be aligned against the magnetic field. And we'll call those spin up versus spin down. So the population then for our up case, our population of spin up or +1/2, we define that as the number of nuclei that are in that spin up, that +1/2 state, divided by the total number of nuclei. As we're dealing with hydrogen, that's the total number of protons in this case. So this is defining our population based on the number of nuclei that are spin up over the total number of nuclei. And we do the same thing for the population of spin down. We're just looking at the spin down compared to the total number of nuclei. In this case, since we can only have spin up or spin down because they're fermions, they only have these 2 spin states, then that means that in this case, our total number of protons has to be equal to our number of spin up protons plus our number of spin down protons. It also means that our our total population, if we add together our two individual spin up and spin down populations, that this would be equal to our number up plus our number down, and both of those would be divided by the total number n, which is equal to our n up plus n down. So that should, it has to go to 1, is basically where that comes into play. So we add these together, the populations have to equal 1 because the total number of nuclei is equal to the possibility of being in one of only 2 possible spin states. Our polarization, I'll use a big P to define polarization, is in this case for the proton equal to our difference of our spin up population minus our spin down population. If we write this out kind of similarly to how we did the total here and put it in terms of the n's, now we've got n up, the total number in the spin up state, minus the total number in a spin down state, divided by, both of them are divided by n, which is equal to n up plus n down. This type of equation might look familiar to some of you. This is a type of asymmetry. In fact, we'll talk more about asymmetries related to cross sections a little bit down the road, but just kind of introduction, when we're talking about polarization, we're really looking at the asymmetry of spin up compared to spin down, normalized by the total number of particles in our sample, the total number of nuclei in our sample. So keep in mind that term for asymmetry, we'll come back to that later. So most of the polarization that you're likely to encounter in our field in JLab physics will mostly be of this spin half and be defined like this. We can also look at it not just kind of in these this definition related to the total number of nuclei, but we can come to the same conclusion for polarization if we look at it through quantum mechanics and expectation values as well. Basically, you can look at it either way, and we end up with the same result. So if we do it quantum mechanically, what we're looking for is where the polarizations equal to the expectation value of the z component of spin compared to the total spin. So what do I mean by that? So quantum mechanically, for a spin 1/2 particle, and I will also write this as p sub z with 1 z here. We'll mention why in a minute. But this would be equal to the expectation value that our z component our expectation value of the z component of our spin compared to the total spin of our system of nuclei. This turns out to be identical to that same definition that we already written as the population up minus the population down. Putting this 1z in here, almost every time you hear about polarization and only polarization, it's almost always talking about a spin 1/2 particle. If you're in my world, I would call this vector polarization. I'll mention why in a minute, versus just polarization. Because it turns out that this type of polarization is not the only kind of polarized particle that we can have. But it is, for really JLab physics especially, the most likely type of polarization that you'll see. However, like we mentioned earlier, we don't only have spin 1/2 particles. We also have particles with higher order spin. So if we look at particles that have spin greater than or equal to 1, then we need more than just this term to describe the spin state. Remember, when we were looking at the spin 1, it had an up state, a down state, but also a spin 0 state. And this term would only describe an up and a down state. So for a spin 1 particle, the polarization of spin 1, we can define one term of its polarization, the vector term, the same way that we define the polarization for spin 1/2. So we would still have the same expectation value of the z component of our spin compared to our total spin. And this would give us a population difference of up minus down. What's different here, though, is this up and down that I'm kind of drawing these arrows a little more explicitly. This was, spin up was our plus 1/2 minus our minus 1/2 state when dealing with a proton. With a spin 1 particle, like say the deuteron, this is now looking at the population of the plus 1 state minus the population of the minus 1 state. So these terms can look the same, but there's a little bit of a difference between them. It does mean that in this definition, we don't have the spin 0 state at all here. So we don't have our full definition of what's going on with all the different spins in a spin 1 just from the vector polarization. In order to get the rest of the spin, we need to define what's called a tensor polarization. And that tensor polarization, hopefully, will give us information about that spin 0 state that our vector polarization didn't tell us anything about. So for a tensor polarization, and tensor versus vector is coming from when you do the matrix multiplication to get your expectation values, that's where the difference in terms between a vector multiplication versus a larger tensor multiplication comes into play. So the tensor polarization is often written with 2 sub-z's for spin 1 particle. And this is now a little bit more complex expectation value, not just the pure expectation value, but it's the expectation value of 3 times the z component of our spin squared minus our total spin times total spin plus 1. So this whole expectation value, which comes from the tensor multiplication term. And then we divide this by the total spin squared. When we run our math through here for our expectation values and turn it into populations, like we did for vector polarization, we find that the tensor polarization is equal to 1 minus 3 times the population of the spin 0 state. So what the vector polarization is giving us really is direct information of the spin 0 state, whereas the vector polarization is giving us the difference between the plus 1 and the minus 1 spin states. If we did this, if we try to do a tensor polarization for a spin 1/2 particle, which I mean, there's nothing to stop you from doing the math for it, what we would find is that our tensor polarization for a spin 1/2 particle is just always going to be equal to 0. And the reason for that, if we look at our expectation value terms here, so we look at our first term here, our 3 times our z component squared, for a spin half particle, the Z component could either be +1 half or -1 half, and that's it. So we'd have 3 times either plus or minus 1 half. But if we square that term, we don't care if it's plus or minus, meaning that this will always come out to be 3/4. And if we do it, our second term here that we subtract from that are I times I plus 1 for spin half would give us a 1/2 times 1/2 plus 1. We run the math through on that. That's also going to give us 3/4. So we'd have 3/4 minus 3/4. Our tensor polarization for spin half is always being 0. Sometimes, if you're looking up tensor polarization in the literature, I'm doing a lot with tensor polarization now. I think it's a really exciting topic. We'll kind of building up. We'll talk about why in a little bit once we kind of do a summary of polarization. But you might also see tensor polarization sometimes referred to as alignment. So if anybody's doing any literature reviews on tensor polarization in particular and come across the term alignment, it just means tensor polarization, and it's a different way of just saying the same thing. And instead of the PZZ, you'll also see it sometimes written as just a capital A. But it's basically all saying the same thing. We could also use the fact, if we go back to our spin 1, so let's get rid of our spin half toy here and go back to our spin 1 particle. Just like in the case of the proton, when we added up all of the total possible populations, it had to equal 1. For a spin 1 particle, we now have 3 different possible populations, not just 2. So the population of our +1 state, plus our population of our 0 state, plus our population of our -1 state would have to equal 1. We can use this definition along with this term here if we solve this for we can solve this for p. We solve this for 1 and throw that into here. We can write this tensor polarization a slightly different way, which is actually the way that I prefer to write it, as the population of our +1 state plus the population of our -1 state minus 2 times the population in the 0 state. The reason I like to think about it in these terms is for the deuteron in particular, which is where I'm doing a lot of work with tensor polarization right now. The physical structure of the deuteron in the +1 state and the -1 state is spatially identical, just the direction of spin is flipped. And in both of these cases, the deuteron kind of has this almost peanut-like structure to it. But the structure when it's in the spin 0 state maps out, instead of this kind of barbell or peanut-like structure, runs a toroidal or donut-like structure. So I like to think of tensor polarization of, do you have more peanuts or do you have more donuts? But basically where it's coming from is, this is relating our spin 0 term, and along with our tensor polarization and our vector polarization, we need both of them for spin 1 to describe all 3 possible spin states. Versus with spin half, we only need the vector to describe all the possible spin states. Whoa, now my board is falling apart. Now everything is falling apart. Exciting. How exciting. All right, let's fix that in a moment. Apologies for technical difficulties. Everything is stacked on books at the moment. It's actually my first time using this equipment setup in my office here at the University of New Hampshire. I've been remote all year so far, and it's a slightly different setup, is apparently not quite as stable as what I'd done over the past year. But that's okay, we recovered. Apologize if that was loud on the microphone for anyone. right, so let's do a summary then of my markers. I'm not swapping them out. A summary for our polarization. What polarization is going to tell us is how many spins are in some particular spin state, whether it be +1, -1, 0, or +1/2, -1/2. So our spin half polarization, like we said, is the same as this vector polarization of our +1 population minus our -1/2 population. In this case, if we say that a target is unpolarized, what we mean when it's unpolarized is that there's an equal number of nuclei in the +1/2 state as there are in the -1/2 state, that these two populations are equal to each other. So that our +1/2 is equal, our +1/2 population is equal to our -1/2 population. And since we only have two possible spin states, both of those would have to be equal to 0.5. And if we do 0.5 minus 0.5, that would give us a total polarization of 0. So for spin half, when we're unpolarized, this polarization is equal to 0. See, a quick question, is tensor polarization related to some element of spin matrix for spin 1? Yeah, it's actually, when you're doing the matrix multiplication of the different possible spin states, in order to get out those expectation values, the vector term just takes the place of a simple vector multiplication, whereas the tensor term relates more to the cross products between them. So that's where the tensor and tensor polarization comes from. And that leads to that more complicated definition of that second expectation value. Back to our summary. So we look at unpolarized would be p equals 0. We can also have positive polarization. And in this case, we have more nuclei in the spin 1/2 state than we do in the minus spin half state. And that leads to a polarization value that is greater than 0 and less than or equal to at most 1. Sorry, I moved my hand out of the way. So for positive, when we say we have positive polarization, our p is greater than 1 means that we have more nuclei in the +1/2 state versus the -1/2. And then we can do the same thing for negative polarization. As you might imagine, that says that our -1/2 has more in it than our +1/2. So that means that our polarization would be less than 0 and could go down to a minimum value of -1 in the case of spin 1/2. If we look at not just spin 1/2, but go to spin 1, we can look at the different cases here as well. But now we have to keep track not just of vector polarization, but tensor polarization as well. So if we do spin 1, our vector polarization is equal to our population in +1 minus our population in -1, and our tensor polarization is equal to 1 minus 3 times the population in our spin 0 state. So if we're unpolarized for spin 1, this again means that we have an equal number of nuclei in all 3 possible spin states. So that means that the population in +1 is equal to the population in 0 is equal to the population in -1. And since we have 3 here, that means that each of these has to carry 1/3 of the number of nuclei within. So if +1 and -1 are both equal to 1/3, our vector polarization would be 1/3 minus 1/3 would go to 0, just like we saw before. And our vector polarization is also equal to 1/3. When we multiply that by 3, this becomes 1. 1 minus 1 equals 0. So another way that you can think of where this 3 is coming from, other than doing the matrix multiplication, is you could also think of the 3 needing to come in by the definition of unpolarized, being that both vector and tensor polarization have to equal 0. When they're equal to 0, it means we have equal number in all 3 spin states. So that means that by the definition of our tensor polarization, for this to be 0, when this is equal to 1/3, it has this extra normalization factor of 3 out front.
Ellie?
Yes.
There are 2 questions in the chat related to tensor polarization.
Tensor, I think I mentioned the first one already. Second one, how do we define tensor polarization for massless spin 1 particle? For I think for the polarization, you could define it in terms of the populations the same way as you would whether it was massive or massless. I've not looked into that aspect of if you're looking at massless spin 1 particles directly. I just haven't taken a look at that recently, but I'll take a look at that after today's discussion. See if there are any other intricacies that come in from it being massless, and we can mention them in our next discussion later this week. But I think it would be, if you're defining at the population level, that the definition I think would come out the same, but I'll double check that. All right, so spin 1, unpolarized, all our spin states are equal to each other. If that isn't true, our vector polarization is similar to the spin half case, where vector polarization would be positive if we have more in the +1 than the -1, or it would be negative if we have more in the -1 than the +1. And just like in the case for spin 1/2, the maximum bounds of this would go positive polarization from 0 up to a maximum of +1, or for negative from -1 up to 0 for the vector polarization. However, for the spin 0 case, if our spin 0 polarization is greater than 1/3, that means that we have more in our spin 0. It's kind of out of equilibrium in spin 0 compared to the other 2 spin states. And that's going to lead to a negative tensor polarization. It can actually go down to a factor at most of -2 instead of -1 for our tensor polarization. Or in the other case, if our P0 is less than 1/3, then our tensor polarization would go from 0 up to a maximum of +1. So this is the fact that this can go down to have a maximum negative polarization of -2 actually relates back to this definition of 3 that comes from this unpolarized portion here. So remember that other way I wrote the tensor polarization, which is equivalent to what I'm writing, what I wrote here, where I had the +1 population plus the -1 population minus 2 times the 0 population. If these two are, or if you have more in the spin 0 times 2, right, that normalization factor, than there are these, this will go to negative. And because of this factor of 2 here, that's where this comes down to at most a -2 tensor polarization if you have no nuclei in either the +1 or the -1, if all of your nuclei are in the spin 0 case. So you can think, I like to think of the -2 related in this form. Of course, you can do the same thing here, where if you filled up everything so that P0 is equal to 1, then this would be 1 minus 3, giving you -2 as well. So different ways of thinking about the same thing, but they are equivalent to each other. The important thing with tensor polarization is it has a larger negative value that it can go to than vector polarization does. Now I need to, apologies while I refine all of my markers from our minor technical difficulty earlier. So if there are any questions on that before I start erasing things, what we're going to be moving on to next, now that we've talked about, what is polarization, and when you hear the term polarization for either vector or tensor polarization, you now have a sense of how it connects to the different spin states. What we're going to focus on next is how can we use polarization? How can we manipulate spins to create these different spin populations, to create different polarization values that we can then use in nuclear physics applications? So basically, how do we create this imbalance of spins that creates polarization of either greater than or how do we create polarizations that aren't 0, either on the positive end or on the negative end? That's what I'm attempting to say there. So for doing this, mostly what I'm going to be focused on in this talk in particular, based on the topic of our polarized light ions, is how we create those polarized light ions, particularly in the context of polarized targets. And as I mentioned before, I'm a fixed target person, so that's going to be a lot of what I'm going to discuss here. I'm having multiple issues today. That's okay. We'll work through it. So at JLab, if we're doing polarized work at JLab specifically, there's really 3 major common types of polarized target that you're going to see. These aren't the only types of polarized targets that are out there, or even when we get into experiments, we're talking about the different kinds of experiments we can do with polarized target. But for JLab physics especially, there are 3 common polarized targets that we'll use. And these are, the first one is called spin exchange optical pumping. I'll describe all these terms in a little bit. We'll go into each one of these in detail. The shorthand for that is SEOP. And spin exchange optical pumping. And this will polarize particular helium-3. So that's one major type of polarized target. The second major type of polarized target is called dynamic nuclear polarization. Or DMP, and this is the kind of target I'm currently building here at UNH. Dynamic nuclear polarization is really useful for polarized deuteron, polarized proton, polarized nitrogen, lithium, a number of other types of polarized targets. But not helium-3. We can't do helium-3 with DMP versus we can do it with these other types. And the third type that we'll talk about are frozen spin targets. And where these are the acronym for the major one at JLab right now is taking the FRO from frozen and then ST for spin target to create the acronym FROST. And this is really useful for polarized proton. Actually, we'll find out as we kind of go through the detail, the frozen spin target is really a subcategory of dynamic nuclear polarization. But there are some differences between just kind of general DMP target compared to a frozen spin target that are important, and we'll discuss what those differences are. For each of these three different types of targets that are common for JLab physics, each one has its own unique strengths to it. And then likewise, its own unique issues where it doesn't work as well for, but things where it works really well for. The first one of these, the spin exchange optical pumping, as I mentioned, that lets us polarize helium-3. And the reason why helium-3 is really interesting to polarize is that our helium-3 nucleus consists of 2 protons and a neutron. And if you have this in a polarized state, the vast majority of the time, the 2 proton spins will cancel each other, meaning that the entire spin of the nucleus is carried just by the neutron. And that happens on the order of approximately 90% of the state. There are higher order states where that's not true, but the majority of the time, if you polarize helium-3, what you've really done is polarize the neutron inside of helium-3, which means that SEOP, spin exchange optical pumping, is particularly useful for probing the neutron. Since we can, by polarizing helium-3, we're basically polarizing the neutron within it. There are higher order complications because it's not a free neutron, which do come into play and have to be accounted for. But that's the major benefit of the spin exchange optical pumping technique. The DMP targets, what they're particularly useful for are probing especially the proton and the deuteron. It can do, nitrogen higher nuclei as well, but it's really used at JLab at least most heavily for studying the proton and the deuteron physics. Especially what's useful here is DMP targets tend to be higher luminosity targets than other types of targets like spin exchange optical pumping. The reason why it's higher luminosity is DMP actually, the target material is in a solid state. So you have a denser form of the material that you're using as your target than for spin exchange optical pumping, which is in a gas form, so it'll be less dense. So DMP gives us a higher luminosity because it's in this solid state. However, one of the downsides to it is that it needs a very large external magnetic field in order to operate. We'll talk about those details in a little bit. But that's one of the downsides to DMP. It's requiring this large magnetic field, especially depending on how that's oriented with an incoming beam. If you have your target magnetic field transverse to your beam, then your beam of electrons, which are charged particles, when they go through that magnetic field, they're going to get bent by it. So that field will extend, ideally it's just around your target, but it'll also have fringe fields outside and you would need to track how the electron is going to propagate through your target field and then pre-account for that, especially in the transverse case, leading to really trying to pre-bend an electron beam to account for how it's going to enter and be deviated from the magnet. So that's one of the downsides of needing using DMP, especially if you're doing transverse types of targets. This is where frozen spin targets like Frost can come into play, because these don't need nearly as large of an external magnet. So these can probe protons without this large external magnet. But the downside to the frozen spin targets is that they need either extremely low current electron, and even then it probably won't work very well, if at all. You're really looking at limiting your type of beam into a photon beam. Question, what order are the magnetic fields? For DMP, we're looking at magnetic fields on the order of between about 2 Tesla up to about 7 Tesla. Spin exchange optical pumping does have some magnetic field, but it's on the orders of, I think, a few hundreds, maybe 1,000 at most Gauss. It's a lot, significantly smaller magnetic field than for DMP, so that the spin exchange optical pumping targets don't require this kind of pre-deviation. It's really the DMP where that 2 to 7 Tesla magnet comes into play that really starts to move things apart. Question, how do we polarize photons and electrons? When we are done talking about the polarized targets, I'll do a little bit talking about polarized beams, such as the photons and the electrons. We probably won't get to that today in the next half hour or so, but we'll talk about that later this week. As I mentioned, these are kind of our 3 major types of polarized target that we use at Jefferson Lab. And there are other kinds as well, but I'm going to take a look through all of the comments that you provided earlier for your different experiments and parse through those to see if there are any other targets that might be of interest to you. And in fact, if there are other targets beyond these 3 that you expect to use, feel free to throw that into our Slack channel as well. And I'll take a look there, and I can add those into our discussion for later this week. But for now, at least, these are going to be the 3 that I'm going to focus on. So let's start with this spin exchange optical pumping. So the way that this kind of target works, apologize, I am trapped in my chair a little bit. There we go. For spin exchange optical pumping, we start with circularly polarized laser light that we use to drive the polarization of helium-3. And we talked about what polarization is. We can derive that positive and negative. You might also, if you're into this kind of physics, polarization we've been talking about so far is also sometimes referred to, especially outside of nuclear physics, as hyperpolarization. And what's meant by hyperpolarization is just that some mechanism, be it spin exchange optical pumping or dynamic nuclear polarization, some mechanism has been introduced that causes a polarization greater than you would get if you just put something in a magnetic field. As like we said before, you put any of these nuclei in a magnetic field, there's going to be some of them that align one direction versus another, and depending on that magnetic field, you will get some amount of base polarization. So hyperpolarization is basically going beyond, doing some process to drive the polarization higher than you would get if you just used a magnet to do polarization. you'll usually tend to see that term, usually not so much in our community, but a lot of polarized targets are finding applications outside of nuclear physics in medical research, in especially doing different kinds of body scans. Polarized targets, nuclear physics generally, but especially polarized target and medical imaging have a very long connected history. If you're reading anything in the medical imaging community, you'll almost always see the hyperpolarization term. But anyway, it just means what we call polarization in nuclear physics. Okay, I diverged a little bit. Back to spin exchange optical pumping. So we have circularly polarized laser light, and we're going to use that to drive the polarization of helium-3. Downside is, with polarized light, we can't do this directly. So we want to polarize the helium-3, but we can't do it directly. So why not? What's happening here? Well, what the light is chosen at particular frequencies such that it will drive transitions not of nuclei, but of electrons. And then through collisions with nuclei, the electrons would transfer some of their angular momentum to the nuclei that over time would build up an amount of nuclear polarization from an electron polarization. But in the case of helium, for any helium, helium-3 included, the electrons that we have in helium, we have 2 electrons in a closed shell. Meaning we can't drive any spin transitions because we've already closed off the electron shell that we would drive to higher order transitions. So the laser light can't directly do it on helium-3 itself. So instead, there's a workaround that we use. What we'll do instead is introduce some alkali metal that has electrons that can be put into higher spin states from the laser light. And when we're talking about metal in the case of spin exchange optical pumping, we're not talking about solid state metal. We're talking about a gas of metal atoms. So part of these kinds of targets, in order to help maintain the metal nuclei in here, these alkali metals as a gas state, you'll see these targets often put in an oven in order to bring their temperature up, in part to ensure that we stay in this gaseous state. If we take a look at the different alkali metals, we could look at what frequency of laser we would need to drive different spin transitions, which are going to depend on the different shell states of the different nuclei we're looking at. So basically what we want, we have a number of different energy levels, and we feed in light that is at the right frequency to induce a transition up to a higher order. And because of quantum mechanics, you have to do things in these discrete values. So we can find what type of laser light we would need for different types of alkali metals. Due to the availability of different lasers, the one that is most easily available to get the high-powered lasers that we need in order to get the electron polarization up to then collide with eventually getting to helium-3 polarization, we end up mostly having lasers that will polarize rubidium. So if we're looking at alkali metals, the far left-hand side of the periodic table, looking down on that row. So rubidium is typically used because we can find lasers at high power. Lasers are available for those frequencies. The downside to rubidium is that, and we mentioned before, we're polarizing the electrons, but what we want are the nuclei to be polarized. So through collisions, you can calculate out what the cross section is to transfer the angular momentum from the electrons to the nuclei to spin those. And it turns out rubidium is useful because of the lasers being high power, but is not as good for the collision transfer as another alkali metal, which is potassium. So potassium has a better spin exchange rate. And it also has a better spin relaxation properties as well. So spin relaxation, so if we put our electron into a higher spin state, the relaxation time would be how long it takes to go back to the original state. And if that time is short compared to the nuclei we want to polarize, then we can use the same electron over and over and over again to polarize more nuclei to build up a large polarization. But if the spin relaxation time is long compared to this, then we can't use the same electrons over and over and over again. So potassium has these a better probability to cause spin exchange and a better spin relaxation, but it's much harder to get lasers available that will do potassium directly. So even though these two things come into play, the fact that we can't really use potassium directly, there is a technique that utilizes both of these to try and take the advantages of each to create a polarized target. And this is, you'll see referred to as hybrid spin exchange optical pumping. So in order to kind of get the best of both worlds here in our hybrid spin exchange optical pumping, what has been done is doing a combination of both rubidium and potassium to drive large helium-3 polarization. So the first step is to use lasers, the circularly polarized lasers, to polarize a low density rubidium gas. So that's step one, is we use the lasers that we can get the right frequencies and powers of pretty easily to drive the rubidium transitions. There will be some interaction of the rubidium with helium-3 to drive some amount, but the interaction between rubidium and potassium, it turns out, is higher than that directly of rubidium and helium-3. So once we have these polarized rubidium atoms, they will transfer their polarization to a higher density potassium gas. And part of the reason we wanted that low density rubidium is going to be related to the spin relaxation effect, and we can have a higher density potassium here, in part because of its lower relaxation rate. And also that the potassium is going to be interacting both with the rubidium and with the helium-3. So through collisions, so we transfer the polarization to potassium via collisions, and then the potassium transfers polarization to helium-3 through more collisions. So kind of we draw a schematic of what we're doing. The first thing that we want to do is put rubidium nuclei into a particular spin state. So let's say we want to put rubidium into a spin up state. So we'll use our circularly polarized laser light to polarize the rubidium. And so there will be some amount of collision of rubidium with helium-3 that will exchange the angular momentum. So the rubidium will flip its spin, which induces the electrons in rubidium flip their spin, which induces the nuclei in helium-3 to flip their spin. But this only happens on the order of about maybe 3% of the time. Much more likely, so this is kind of one process that can happen, but not as likely to occur, as the rubidium interacting with potassium. So once again, the rubidium goes through a spin flip, driving a potassium spin flip. And then this potassium, that's now in the state we want it to be, interacts with helium-3, that's not in the state we want it to be, to get it in the cause a spin flip for both of them by exchanging their angular momentum. And this happens, this process will occur at a much higher rate than this initial process of the rubidium directly to the helium-3. So what does this look like, when we actually build these targets?
So Ellie, we have about 8 minutes left.
All right, perfect. I'll do a quick drawing of what these targets look like, and then we will pick up next time and leave some time for questions. So I mentioned we have this this oven that we put these things in order to heat up our gases. So there's usually a large ball that is inside of an oven to heat it up and allows laser light to come in. And this is called the pumping chamber. And older versions of this target would have this big spherical pumping chamber connected through a small tube to a very long tube that would be in the path of an electron beam. More modern versions are basically the same thing, but they've replaced the single tube here with two tubes coming off the sides and trying to get them as close as possible to the edges of where the physics occurs. And the reason for changing from the one tube to the two is as the electron beam comes in, it's going to heat up one side more than the other, which is going to drive a convection current through this entire system, meaning that you'll get more nuclei into your pumping chamber than to come back down, and then back into your pumping, and then to come back down, to drive higher polarizations than you can get with just that initial one. And in fact, in this case, we can get helium-3 polarizations greater than 70%, which, we talk about it in terms versus 1. That would be saying that our polarization of helium is greater than 0.7, basically saying that same thing. So this is a good place to, I guess, stop for today, if there are any questions. Yes, Christopher.
Yeah, that last bit with the helium polarization bit, is that the actual target that is being bombard, like in the target chamber, being hit by the electron beam as it's going through?
So the
Or I
part
guess-
on along the bottom, that long tube on the bottom, is where the electron beam would travel through.
And so then how do you not have a whole bunch of contamination with then the potassium and rubidium going through that? Okay.
And in fact, these types of contamination need to get taken account for. When we started looking into doing cross sections with these polarized targets, I'll talk about things like dilution factors. I mean, that's more for DMP, but it's a similar, there's contamination factors where we have to account for how much rubidium is there, how much potassium is there that would be affecting our results, that we need to make sure that we're accounting for that after we get our data. So that's part of our post-analysis, is to really study how much of each of these nuclei would have been in the path of the electron beam, and then figuring out how can we account for removing them from our actual physics that we're interested in.
Okay, that makes sense. Thanks.
Yeah.
Okay, Catherine.
Okay, hi. So you said that that first reaction that you drew where the rubidium directly hits the helium and flips it, that happens like 3% of the time. And then you said that when the rubidium hits the potassium, hits the helium, that happens at a higher rate. Is that 97% or is there another
So
thing that happened?
the rubidium to potassium is getting close to the remaining, like what, 97-ish percent, so close to 100% of the time.
Sure.
And then the secondary after that, I think, is on the order of, I think this might be for the older chamber, not for the newer one, but I think for the older chamber, the estimate is about 25-ish% of the time for that
Okay.
secondary. So it's happening a factor of 10 times more, basically, than the direct rubidium helium-3.
Okay,
At least in
so
the older target. I think that's increased with this new convection mechanism, but I don't have the full details for that.
if so in this whole process, then do you always polarize the helium?
You're continuously doing it. Yeah, you're always
Oh,
constantly
got
pumping.
it. Okay. Okay, thank you.
Yeah. There is actually a Helmholtz coil put around it to help hold the polarization in place once you have it, which particularly helps with the spin relaxation to increase the relaxation time of your helium-3.
Okay, yeah, that makes more sense. Okay, thanks.
Okay, Mateo.
When you introduced the SEOP, you said that it's useful for proving the neutron because the entire spin of the nucleus is carried by the neutron.
Yes.
But I don't really see this. It's something related to a model, or is something related to an experimental come out? I don't know.
This is related to the ground state orientations of helium-3 as a nucleus. So its lowest ground state is where the proton spins are oriented against each other. And then all the remaining spin is carried by just the neutron. And when you do the total ground state, that part of the ground state is approximately 90% of the ground state. And then the remaining part of the ground state would be where the protons are not anti-aligned, they'd be aligned together. So you'd be really flipping one of the protons instead. That happens on the order of, I'm trying to remember off the top of my head, somewhere between 5 to 7%. I think 7-ish% for that one. And then the first highest order state is another state where the proton will get the spin flip instead of the neutron, which I think is on the order of 3 to 5%. So it's looking at those two possibilities for the ground state plus the next highest state of helium-3 as a nucleus. But if you take those three things into consideration, which are the three highest order parts of helium-3, when it's in a fixed target, about 90% of the time, roughly, you end up carrying, the neutron is carrying the spin of the entire nucleus.
Okay, thank you.
Okay, Daniel.
Yeah, so when you say that the helium reaches 70% polarization, is that the steady state result of you're continuously trying to polarize it, but also it relaxes and you can only hold the spin for so long?
Yeah, so I didn't quite get to it today. We'll talk about these effects a little bit next time, but we're constantly driving polarization, but it's also trying to constantly depolarize too. So there's this balance between how fast can you polarize it versus how fast is it trying to depolarize. And the balance between those is where we find what our maximum polarization is when we kind of hit that steady state balance between constantly driving it and it constantly trying to depolarize. And I believe the best number, I might be wrong on this, it's been a little bit since I've looked at helium-3, but I think from what I've seen most recently is that the best numbers for helium-3 polarization on the order of greater than 70%, might even be a little bit higher than that now.
Cool. And I imagine for collision experiments, the maximum polarization is probably lower because it's harder to maintain polarization.
Well, I believe that is with expected beam conditions. So you will have, when the beam is kind of driving things, that will, actually the depolarization from the beam will have some effect. For the spin exchange optical pumping, it's not as big of an effect as it is in dynamic nuclear polarization. We'll talk about the reason for that next time, but it's related to, for spin exchange optical pumping, it's already needs to be at such a high temperature that the beam heating effects are fairly small compared to the oven that you have this whole thing sitting in. Versus a DMP target, you need that to be extremely cold, down to 1 Kelvin or below. So there, any effects from beam heating are extremely important and will depolarize the target for DMP. So it's another one of the downsides of DMP compared to SEOP. Like I said, they have different pros and cons to each of them.
Okay, cool, thank you.
Okay, any other questions for Ali? Alex, please go ahead.
Yeah, sorry, this is more like a language question than a physics question. When you talk about spin of a nucleus, do you talk about the total angular momentum or really the spin? Because they are different in the definition somehow.
For what I am talking about, I am talking about just the spin. So not the orbital, not the total orbital angular momentum J, not the orbital momentum L, but the S part of angular momentum.
Thank you very much.
Yeah.
Thank you.
Yeah, the only one in the near the end of the first lecture today, there was that one part where I talked about the magnetic moment of a nucleus as a whole. That had both orbital and L term and an S term. But I think that's the only point so far where I've talked about the orbital term.
Yeah, sorry, because sometimes it's confusing. Many people confuse that. It was just for me. Thank you very much.
Yeah. No, thank you for bringing that up.
Okay, any other questions for Ellie? All right, I guess not. Perhaps it's time to end this session. So just a couple of announcements before we end today's session. First, Ellie, we also have these social gather town meetings, and you're invited to that. See that a lot of people are interested in talking to you more about polarized targets, and there's a flow of comments here that says that it's a very clear session and they really liked your demonstration, and writing things down really helped put things in perspective for them. So thank you very much for that. And please join us on Gather Town if you have some time after this. Second thing, tomorrow morning.
Everyone, I don't know if I'll be there today, but I should be there for the rest of the week.
Okay. If you have some time, post on the Slack channel, say that you're planning on coming there at this particular time. And
I look at my Slack a lot, so if you do have any questions, Slack is a great way to get a hold of me.
Okay. Second thing, there's going to be a careers talk tomorrow morning regarding CVs and resumes and what to do and what not to do at 8:30. It'll be on Blue Jeans. So right after that, you should have all the tools to be able to put your CV together and be able to apply for the jobs. The deadline for them is the 11th, so you have 4 days to apply for them. So we encourage all of you guys to apply for the job of your choice. And having said that, I think those are the announcements that I have. Alex, do you have any announcements that you want to make?
not for now.
Not for now. Okay. So that's it for today. So hopefully you've really enjoyed the sessions, and we'll see you guys tomorrow at 8:30. Okay. Bye-bye.